Buon pomeriggio a tutti. A questo punto posso darvi il benvenuto a nome del comitato di programma e del comitato organizzatore. We have some people connected from abroad, so welcome to you as well to this special day for us on behalf of myself, but more importantly of the program committee and the organizing committee of this event. Actually, these events. Today, we are formally inaugurating the International Year of Quantum Science and Technology for Italy. And today, we are opening the second National Congress of NQSTI, l'inaugurazione del nostro congresso. NQSTI è distinguished partner dell'International Year of Quantum Science and Technology. Abbiamo avuto il privilegio di inaugurare l'anno per l'Italia oggi con questo nostro incontro. Avremo una presentazione dell'UNESCO che vi faremo vedere a breve. Una giornata per noi molto importante e persone molto importanti parleranno ora per portare il saluto e dare il benvenuto a tutti quanti voi e darci gli auguri, immagino, di buon lavoro. Partirei subito con il nostro presidente, il professor Claudio Pettinale, presidente di NQSTI, a cui darei la parola.
Thank you, Fabio. Good afternoon, everyone. Dear Antonella Pollimeni, that is connected, rector of Sapienza University. Dr. Fabrizio Cobis, representative of the minister. Silvia Koska, Quantera program coordinator, and Professor Alexander Golubov from the University of Twente. Dear members of the steering committee, a steering committee perfectly coordinated by Fabio Beltram, and dear members of the board of trustees, dear research manager, Isabella, and dear colleagues, ladies and gentlemen. I am really honored and proud to welcome you to the second conference of the National Science Quantum Technology Institute. As Fabio said, today is an important date for us. The year 2025 has been designated as the International Year of Quantum Science and Technology, celebrating 100 years since the initial development of quantum mechanics. National Quantum Science and Technology Institute is one of the distinguished partners of the International Year of Quantum. The National Congress will be the inaugural event of the International Year in Italy. If in the history of mankind we have passed through revolutions such as the Iron or Bronze Age, today, the latest generation of technology allows us to respond in a different way and with a different power to fundamental, complex, and extremely interdisciplinary questions. 25 years into the new millennium, we are now facing an unprecedented technological revolution. Artificial intelligence, machine learning, networking of intelligent physical device, advanced robotics, personalized medicine are some of the technology driving change. Transistors, lasers, high-speed internet, supercomputers, and magnetic resonance all have transformed everyday life thanks to quantum technologies. And now we are in the second phase of this great revolution. A great revolution is about to begin. Our institute is a consortium that brings together 20 Italian organizations that carry out competitive and innovative research in the field of quantum science and technology. But with the recently BAC, we are now more than 30. Our goal is to address the entire innovation chain, from the strengthening and coordination of all TRL research to its translation in prototypes, favoring the interface with industrial needs thanks to strong outreach and training programs. 2 years after the launch, I am really very satisfied. Our scientific reports are always being well received and evaluated. Our researchers have asserted themselves nationally and internationally. They have disseminated their results and promoted knowledge of quantum technology in community, schools, and the workplace. Our partnership is a community that has demonstrated the benefits of working in a group, the importance of working together for the common good rather than personal interest, without ever penalizing the rightful ambition of the more mature researchers. To use a football analogy, we are demonstrating that we can win a world competition by playing as a team, helping others when necessary, and making our skills always available. Thanks to NQSTI, our country plays a role in Quantera, a leading European network of research funding organizations, which support the development of quantum technology. And some of our researchers win relevant projects. We participated in ERC project proof of concept, for example, in POCAB, funded by the European Committee. We are organizing master school in order to train new generation of researchers, and this is an activity, a fundamental activity. We are continuously stimulating future industrial innovation in the field by communicating them new ideas and opportunities. We need to merge and to integrate more companies to promote technology transfer to them and funding research projects involving them. We are continually expanding the outreach program to make the quantum science technology more readily available in the society. More than 50 scientific products have now the NQSTI label. Dozens of scientific events have been organized, and we can count hundreds of our participation in international congresses. The number of participants to this congress, to this conference, is very high, and the number of researchers that now is involved in NQSTI is very high. You have done a wonderful job. You have done it for yourselves, but you will certainly have done it for the new generation. And for this reason, and aware of the big work you have performed, I want to wish you, all of you, to have a very great conference. Thanks.
Grazie professor Pettinari, è collegato con noi, ce lo possiamo mettere sullo schermo, il dottor Fabrizio Cobis del Ministero dell'Università e della Ricerca, come sapete la persona che segue tutta questa misura coraggiosamente, e do a lui la parola. Grazie Fabrizio.
La parola coraggio è quella che vi ho azzeccata. Grazie professor Bertman, grazie a tutti. Vi chiedo veramente scusa in modo sincero per non essere lì fisicamente, per fare un intervento anche molto, molto breve. Chi mi conosce sa che non lo faccio perché faccio il prezioso, ma veramente siamo in una fase molto, molto complessa e molto impegnativa dell'avanzamento di queste misure, di questi programmi progettuali. Siamo, come lo sappiamo, entrati tutti nell'ultimo anno di vita dei progetti e gli impegni, i risultati che dobbiamo conseguire sono sempre più complicati e stringenti. Sia sul piano scientifico, e questo progetto è uno di quei progetti, di quei programmi che sta dimostrando e sta confermando la sua altissima qualità scientifica in un tema così profondamente rilevante a livello mondiale, e siamo orgogliosi, devo dire, io personalmente, di essere appartenere ad un'istituzione che ha creduto in questo programma e ha destinato risorse molto importanti a queste attività. E verifichiamo anche con l'ausilio dei nostri revisori, il professor Golubo, che saluto di nuovo, che ci confortano da questo punto di vista. E siamo altrettanto impegnati sul piano più tecnico-gestionale, amministrativo, nell'utilizzo corretto, completo, pieno delle risorse. Ecco perché siamo in questo momento un po' in difficoltà nel presenziare ai vari appuntamenti, perché stiamo in ciascuno dei grandi programmi progettuali che seguiamo, e il vostro è uno dei 30, per cui altro che coraggio, qui ce l'ho proprio in coscienza. Stiamo dietro a tutti perché arrivino tutti al porto di destinazione con una navigazione tranquilla, e quindi ogni giorno stiamo affrontando tutte le questioni con i singoli programmi, numeri da destra a sinistra che spesso non tornano, quindi siamo in grandissima tensione tutti quanti, però è la sfida che conoscevamo, sapevamo che era questo il terreno su cui siamo stati chiamati a giocare. Siamo capaci di giocare, stiamo dimostrando di essere in grado di fare qualcosa che magari questo nostro sistema italiano non era abituato a fare, sul piano della collaborazione, dell'integrazione, della interdisciplinarità, dell'affrontare sfide nuove, di mettere insieme esigenze e obiettivi scientifici con esigenze e obiettivi amministrativi. Stiamo diventando bravi a dare valore al tempo, a fare le cose non semplicemente fatte bene, ma fatte anche rapidamente, che è tutt'altro tema di grandissima importanza. E quindi io credo che se ci guardiamo alle spalle, abbiamo alle spalle 2 anni di un'esperienza enorme che abbiamo fatto noi come amministrazione, credo voi, nel confronto continuo tra di voi e con noi. E tutto questo adesso ci deve motivare per spingere ancora di più e meglio da qui alla fine dell'anno, perché poi dobbiamo prepararci al dopo. Noi non finiremo di parlarci e di confrontarci a dicembre 2025, ma abbiamo ulteriori prospettive, ulteriori percorsi da fare, e li dobbiamo affrontare con quella affidabilità e quella credibilità che ci stiamo costruendo tutti i giorni. Io vi esprimo il mio sincero apprezzamento per il vostro lavoro, lo vedo, lo avverto, siamo molto pesanti, io mi rendo conto, siamo molto fastidiosi, siamo molto noiosi tutti i giorni, eccetera, ma so che capite le nostre esigenze e ci rispondete sempre in modo puntuale e corretto, e vi ringrazio il professor Beltram, la dottoressa D'Apolito, la dottoressa Belfiore, che sono le nostre vittime quotidiane di tutta la nostra azione. vi mando un saluto enorme, vi auguro 2 giornate di lavoro, importanti, e se ci riusciamo magari ci vediamo anche fisicamente domani in qualche spazio delle nostre 24 ore. Buon lavoro a tutti.
Grazie. È vero, è tutto vero, i contatti sono praticamente giornalieri, vi posso assicurare, e se non invitate me chiedete alla dottoressa D'Apolito, che è ancora più adatta di me a darvi queste informazioni, e viceversa è vero quello che diceva il dottor Cobi sul fatto che il contatto giornaliero anche nell'altro senso, perché la quantità di questioni da risolvere è sempre straordinariamente grande, richiede sempre molta energia, e avere un'interfaccia veloce come Fabrizio Cobis, che in questo momento non ci sente, quindi è veramente onesta questa cosa che vi dico, è una risorsa preziosa. Abbiamo adesso il saluto delle 2 ospiti istituzionali per i nostri eventi, che sono la Presidente del CNR, la rettrice di Sapienza. Chiedo quindi la regia cortesemente di trasmettere il video che ci ha lasciato la Presidente Carrozza, che in questo momento, se ricordo bene, è in Costa Rica, beata lei, ma non al mare, in una missione di lavoro. Io ho offerto di accompagnarle e fare tutto questo in remoto, ma non è stato possibile. Darei quindi la parola alla regia. Grazie.
Buongiorno a tutte e a tutti, sono Maria Chiara Carrozza, Presidente del Consiglio Nazionale delle Ricerche, e innanzitutto voglio darvi il benvenuto al CNR. E penso che per noi del CNR sia veramente un grandissimo onore che il partenariato Quantum si riunisca proprio qui per parlare del presente e del proprio futuro, delle ricerche in atto, per confrontarsi anche sulla sfida di trasformare questo partenariato esteso, che va dalla ricerca fondamentale più verso gli aspetti di innovazione, e quindi riguarda un po' anche la trasformazione della scienza in tecnologia e le potenzialità che le ricerche in questo campo possono dare, e che guardi al futuro trasformandosi anche in un istituto nazionale che possa fare networking, connettere, ampliare ed accogliere tutti le scienziate e gli scienziati che si occupano di quantum a tutti i livelli, sia più concentrati sull'hardware, sia sulle domande scientifiche ancora aperte, sia anche destinate all'innovazione, a fondare start-up e magari a cambiare il mondo imprenditoriale italiano mediante la scienza e la tecnologia. Quindi posso dire che il CNR, che è una parte importante anche attraverso gli SPOC e la presenza delle ricercatrici e dei ricercatori della nostri istituti, vuole veramente essere un pilastro strategico, ma in senso accogliente, di questo partenariato, e vuole aprirsi e anche pensare che l'Italia possa essere veramente, attraverso anche il sistema europeo e la partecipazione alle iniziative europee, un paese in cui il quantum possa avere un grandissimo sviluppo. Quindi grazie a tutti voi, saluto il professor Beltram per tutti, che poi estenderà a tutti quanti anche il benvenuto, e a tutte le colleghe e colleghi del CNR che hanno reso grande il CNR in questo ambito. Grazie.
Grazie a nome di tutti alla Presidente Carrozza per il suo benvenuto e per ospitarci anche per questa edizione, e darei ora il video, se non la parola, alla professoressa Polimeni.
Buongiorno a tutti e a tutti, con grande piacere porto il mio saluto e quello dell'intera comunità Sapienza in occasione del secondo congresso nazionale del National Quantum Science and Technology Institute. È un evento di fondamentale importanza per il progresso delle scienze e delle tecnologie quantistiche nel nostro Paese. Questo congresso rappresenta un'opportunità di condivisione e di approfondimento delle ricerche più avanzate in un settore che sta rapidamente emergendo come chiave per l'innovazione in numerosi ambiti tecnologici e scientifici. Le tecnologie quantistiche possiedono un'importanza e un potenziale così straordinari che il 7 giugno del 2024, in occasione del centenario della nascita della meccanica quantistica, l'Assemblea Generale delle Nazioni Unite ha proclamato ufficialmente il 2025 come anno internazionale della scienza e della tecnologia quantistica. Questo riconoscimento evidenzia l'impatto decisivo che queste tecnologie avranno in settori strategici come la sicurezza, le comunicazioni, il calcolo e non ultima la medicina. Per sfruttare pienamente questo potenziale e indirizzarlo verso aree di interesse e di sviluppo per tutta la collettività è fondamentale un impegno collaborativo a livello globale. Sapienza Università di Roma è onorata di ospitare questo congresso in collaborazione con il CNR, due realtà che da sempre rivestono un ruolo di primissimo piano nella ricerca scientifica e tecnologica in Italia e nel mondo. Sapienza, con il suo forte impegno nelle scienze fisiche e ingegneristiche, è orgogliosa di essere spoke leader sotto la guida autorevole del nostro prorettore Sciarrino per la Photonic Platform for Quantum Technologies, una delle principali piattaforme che sono dedicate alla ricerca sulle tecnologie fotoniche quantistiche, che rappresentano una delle frontiere più promettenti per il futuro delle tecnologie quantistiche stesse. Il nostro impegno in questo ambito non si limita alla sola ricerca accademica, ma si estende alla promozione di collaborazioni internazionali, al trasferimento tecnologico, affinché l'Italia possa assumere un ruolo di leadership nel panorama globale delle tecnologie quantistiche. Sono certa che i lavori del congresso offriranno a ciascuno di voi l'opportunità di andare a rafforzare le proprie connessioni e andare a consolidare l'impegno che portate avanti con grande competenza, contribuendo così a valorizzare le istituzioni che rappresentate e andare a garantire un futuro migliore per tutti noi. Vi auguro quindi giornate fruttuose, ricche di nuove sinergie, riflessioni, opportunità che contribuiranno al consolidamento di una rete di eccellenza scientifica e tecnologica sia a livello nazionale che internazionale. Grazie per l'attenzione e buon proseguo.
Mille grazie anche alla lettrice Polimeni per il suo augurio, per il suo aiuto e per ospitarci domani. Come sapete siamo in Sapienza nelle sessioni parallele. We now have fabulous music, not quite. We have now two more speakers. Quantera is an important partner for the whole quantum community in the continent, but is also an important partner for NQSTI. As you know, the last call was accessible to Italian scientists because of the contribution from NQSTI that actually made an agreement with Quantera to make this participation possible. We're working on the same format also for the next call, and we have now the pleasure of having with us the program coordinator of this initiative, Silvia Koska, to whom I give the floor. If you can connect her, please.
Buongiorno. Can you hear me?
Yes, we can, and we can also see you now. Thank you so much.
Good morning, everyone. It's an honor and a great pleasure to be there with you here, unfortunately. But it's also a kind of happiness because I want to say that as a Quantera coordinator, I've been there at the very, very beginning, and Italy was one of the main funders, the cornerstone founders of Quantera. And as you may remember, a decade ago, quantum wasn't that popular as nowadays. So Italy and 4 participating organizations, so to say more, CNR, INFN, and particularly NQST are the partners of Quantera, which is the widest network of research funders in the world. So far, what have we done? So We funded over 500 research teams in Europe in more than 100 projects. So this means that we are the biggest funder when it comes to the in multinational programs funded in R&D in quantum. And moreover, we want to fund more. So there will be some news at the end of my speech, and I will be happy to share with you to unveil some information for the upcoming 2025 year. So before I will say that, let me please also say thank you to those who have been there for years within Quantera, fighting for developments, for funds, and building all that what we have today. So Italy remains one of the main partners in Quantera, but it is, as we say in Quantera, it's all thanks to the people. It's all about the people at the end. So I want to personally thank Professor Francesco Saverio Cataliotti, Professor Saverio Pascazio, Ms. Chiara Mussarelli, and Professor Francesco Tafuri, and many, many more for those who are the partners of Quantera. So as you know, we do not only fund research, but we also are focused on a mapping of public policies, so development of quantum field when it comes to public funds. This is important because if you look at the landscape, what happened over the decade, it is actually the one of the fastest development in the world, in maybe in comparison with AI. And it's going to be even better. So at this very, very last moment, please let me also share with you some good news. So we are planning to continue Quantera with in a project of so-called Quantera 3, and it will be announced in the mid-2025. So I will share with you now the link to the Quantum Horizon conference, so you can check, you can see. It's going to take place in Gdańsk, in Poland, in May, and over there we will share with you some news about the funding opportunities for the next year. So last but not least, I think it is important also to tell you more about what have you learned for these years. And I think that 3 musts when it comes to international collaboration. So first of all, cooperation among partners. That was absolutely pivotal, and it was a fantastic collaboration of the network of quantum research, not only funders, but first of all researchers within Europe that are very well connected, and it's really an honor and a pleasure to work with such a fantastic community led by the Quantum Flagship Initiative and Professor Tommaso Calarco. Then the second must is definitely the financial commitment coming from the funders, so member states, ministries, agencies, but mainly also from the European Commission. And this is critical. And here the third must is the quantum strategy that hopefully will come this year, as it was a few days announced within the compass of the EU. So that would be all in order to fund those fantastic research. As you know, you're the best in the world, and let's keep Europe in the forefront and fund more excellent research. So I wish you a very good time, discussions, fruitful discussions, and hopefully looking forward to fund more research. Thank you very much.
Thank you very much, Silvia. Noted. We took note of the message of these new opportunities coming up. The last speaker is the last speaker because he asked us to be the last speaker. It's Professor Golubov. He is the coordinator of the group which is monitoring the activity of NQSTI. As you know, each of these programs has got a monitoring group that receives all our reports frequent reports, I should add, so that they can monitor the activity of the different groups. For us, Professor Golubov and the other members of the committee are a real resource, and I want to thank him very much for his help. Just to give you one example, if you allow me, Alexander, when we were supposed to appoint the committees that were to select the cascaded funding, we asked their help. And it was very important for us to count on their expertise, and they decided who the referees would be to make sure that the whole process was perfectly linear, transparent, and clear. And this is just one example of the many times where they did more than they were actually supposed to be doing just to support us and have us work better. So thank you very much, Alexander, and the floor is yours.
Thank you very much. Good afternoon and buongiorno. Unfortunately, I cannot be present at your meeting, but I attend distantly, and I say just a few words on behalf of the committee, which I represent myself and Professor Jan Kiesman and Professor Ferruccio Renzoni. And from the very beginning, it's about 3 years ago when I got the proposal to evaluate, it was immediately clear that it's an extremely strong proposal, and I was very happy that Italian government made such initiative. It's a big investment in the quantum technologies and fundamental science. Therefore, I'm also happy to join the project somehow as an external expert. We get every quarter reports from you, and it's really a huge amount of work, I must say, very impressive, and a lot of excellent groups with very nice results. And so I'm sure that well, in the remaining time you will demonstrate also some more on application side. Yeah, because it's so far we see a lot of fundamental research, and the final goal is, I understand, this new institute to really to do some more for applications. Yeah, and maybe as a very small critical remark, if I'm allowed, which we made in our recent report with my colleagues, that we get a lot of nice results from you, but in some sense it would be better if they're more correlated to some joint final goal. So that's kind of what I wish you, with the remaining time, to focus more on interlinks, relations between different groups. So, but it doesn't mean that there was no any criticism as such, and we always give you excellent grades, as you know, for the reports, and because it's really very good science. And just to finish, I can say that I'm happy that in Italy such a project is goes on, is running. And okay, thank you for your attention. Yeah.
Thank you very much to Professor Golubov for his words. I will shortly show you the last reports and also tell you what is the reaction that they have made to this precious suggestion from our referees in terms of actions. So this concludes the opening session. Thanks to all the contributors to this important session. We now have a small digression because, again, today we are opening the International Year of Quantum Science and Technology in this country. We are one of the distinguished partners of this initiative. Together with, we're in good company with IEEE, D-Wave, Quantum, and so on and so forth. This you will also see in the movie that we'll be showing in a second, which was the one prepared by UNESCO to start the year. It is a short movie, don't worry. We'll just make a couple of comments on it at the end. I just want to draw your attention on one aspect, and I will repeat this for sure because I think it is crucial. The reason why the United Nations made 2025 the year of quantum is not because of the nice physics that we make. They really don't care. What they're interested in is the impact that all this can have on society. This is a true game changer for innovation on the planet. That is the perception. That's why this is important. And I would like you to learn also from this presentation what is quantum technology, because many of us are so focused on their own work that they all think they can define what quantum technology is, what is the precise perimeter outside of which there's no quantum technology. It's not like that. It's much broader, and that's why it is important. So I would like to ask to please show the movie to all of us, and then we'll make a few comments about it. Grazie. Facciamo il filmato, per favore. Il filmato è breve, abbiamo la soddisfazione che nei, non so, 220 paesi in cui verrà mostrato NQSTI apparirà per 220 e tante volte, questo ci fa comunque piacere. Questo è un po' uno spoiler, questo è successo ieri, ieri c'è stata l'apertura mondiale che è avvenuta a Parigi. Noi avevamo uno stand e per noi era presente un gruppo di persone, tra cui Elisabetta Palladino, che come sapete è la coordinatrice dello Spoke 9 su Outreach and Education. Quindi chiederei a Elisabetta se ci dice brevemente quello che noi abbiamo in mente come attività di NQSTI per quest'anno qui collegato all'anno internazionale. Grazie.
Sì, buon pomeriggio a tutti. Uno dei temi che è stato trattato ieri riguarda proprio lo sviluppo, la comprensione delle tecnologie quantistiche, il public engagement e l'education, il ruolo di questi due elementi che è fondamentale e che è stato sottolineato appunto a diversi livelli. In questo contesto su public engagement e su education NQSTI ha appunto uno SPOC che cura queste attività e è importante che in questa occasione siate tutti un po' informati di alcuni highlight di attività che specificamente abbiamo in programma e che abbiamo già avviato proprio in occasione dell'International Year of Quantum. Innanzitutto potete già trovare sul sito web una rubrica, la possiamo chiamare così, che si chiama Weekly Quantum, alla quale tutti quanti possiamo partecipare. Consiste nel pubblicare settimanalmente un post che può essere su un evento, un anniversario relativo alle tecnologie quantistiche e il ruolo di questa rubrica è quello di coinvolgere un po' tutti in maniera dinamica, quindi chiunque tra voi ha il piacere di contribuire, questi contributi vengono firmati da chi li propone. E altro evento che speriamo abbia una grande risonanza è un Quantum Art Festival che stiamo organizzando. È un festival che si propone di coinvolgere persone, professionisti del mondo dell'arte o anche professionisti come gli studenti delle accademie, e l'obiettivo è proprio quello di proporre una sorta di concorso. I dettagli sono in fase di organizzazione e che si concluda poi con una mostra, con la pubblicazione su un volume su quello che è stato proposto. Anche su questa attività, per quanto sia un'attività di Spock 9, il contributo di tutti è bene accetto, quindi chiunque abbia dei suggerimenti, dei contatti o voglia unirsi al gruppo di lavoro che sta svolgendo questa attività può farlo e ne saremo felici. E oltre alle attività di outreach, e queste sono solamente alcune più nuove che ho voluto menzionare, abbiamo diverse attività di formazione a diversi livelli per la scuola superiore. In particolare abbiamo organizzato delle scuole rivolte estive agli studenti delle scuole superiori, ce ne saranno 3 che si svolgeranno a Como, a Pavia e a Napoli in tempi diversi. Ci sarà una scuola di training per gli insegnanti che si svolgerà a luglio, ci saranno delle scuole per dottorandi, e in particolare una si svolgerà a Catania e un'altra si svolgerà a San Benedetto del Tronto sulle tematiche diciamo piattaforma tecnologica e fotonica e atomica. E in più dal punto di vista della formazione abbiamo avviato sia un master di secondo livello in scienze e tecnologie quantistiche a Catania, ci sarà un minor che verrà attivato a Napoli a fine di quest'anno, e stiamo supportando tirocinanti che svolgano attività appunto presso imprese quantum. Quindi questo in estrema sintesi, e sentitevi liberi di contattarci o di collaborare con lo Spock 9 per tutte queste attività. Grazie.
Grazie mille a Elisabetta. Ora in circa 5 minuti dovrei riassumervi i 2 anni di attività e parlare delle prospettive. Non so se sia ragionevole questo obiettivo, ma farò del mio meglio per dire l'essenziale molto, molto velocemente. Abbiamo una grossa responsabilità, tutti collettivamente. NQSTI rappresenta il 51% dei fondi in questo momento ministeriali esistenti in questo Paese, quindi questi sono dati del Ministero. Quindi far funzionare bene questo schema e utilizzare bene queste risorse è un compito importante, è un compito che è sulle nostre spalle collettivamente e del quale spero siamo tutti quanti consci. Il Ministero lo è, vi assicuro, giustamente anche. Noi abbiamo promesso cose importanti, abbiamo promesso delle cose significative, di raccogliere una comunità, stimolare l'ammodernamento delle risorse di questa comunità, portarla a essere più competitiva, generare interfacce con lo sviluppo industriale del Paese, eccetera, eccetera. Vi ricordate forse questa slide che abbiamo mostrato l'anno scorso? È quella che dice tutto il range delle cose che abbiamo messo in cantiere. La ricerca, l'outreach, i programmi internazionali, Quantera è solo un esempio, favorire la formazione e l'acquisizione di nuove imprese, portare il quantum e l'innovazione nelle piccole e medie imprese italiane che ovviamente non possiamo immaginare abbiano le risorse per sostenere autonomamente questo tipo di innovazione in rapporto con le grandi imprese. E siamo partiti così, con qualche mal di pancia naturalmente, perché siamo partiti in 20 istituzioni, che erano ovviamente troppo poche, ma il bando quello diceva. Abbiamo detto dall'inizio che ci saremmo impegnati a crescere, ad allargare e includere tutte le competenze disponibili. L'abbiamo fatto con i bandi a cascata. E NQSTI è passato da questo, pallino rosso Spoke, questione amministrativa, pallino blu partecipante, le 20 istituzioni iniziali. Dopo i bandi a cascate siamo diventati questo. 32 istituzioni di ricerca sul territorio nazionale che sono entrate nel nostro progetto, sono diventate parte, le abbiamo tutte invitate a diventare parte attiva, soci del consorzio. Alcune stanno lavorando in questa direzione, sono quelle che stanno tra il blu e il giallo, quelle che sono più o meno in transizione, stiamo facendo i passi per portare a questo allargamento. L'idea è di avere potenzialmente, sperabilmente, tutti gli attori rilevanti all'interno di NQSTI, attivamente all'interno di NQSTI. Avevamo detto che avremmo messo in pista 322 ricercatori e reclutato 94 più 10, sono dei dettagli interni al sistema, 104 ricercatori nuovi. Così abbiamo fatto, abbiamo reclutato i 104 ricercatori, abbiamo coinvolto con i bandi a cascata altri 145 ricercatori, siamo a 575 ricercatori coinvolti in questo momento nelle attività di NQSTI. Siamo una struttura grande, abbiamo un grande livello di competenza. Nei primi 2 anni abbiamo prodotto qualcosa come 1 migliaio di pubblicazioni su riviste internazionali, se vogliamo guardare uno degli indicatori, ma come avete sentito anche negli altri interventi non è l'unico indicatore, è un indicatore importante, ma è solo uno degli indicatori. Avevamo detto che avremmo pubblicato 23 bandi, abbiamo pubblicato 23 bandi effettivamente, e questo ha ingrandito ulteriormente perché sono entrate anche le imprese vincitrici di questi bandi. Adesso siamo una cinquantina di istituzioni complessivamente dentro il perimetro del partenariato, se includiamo anche le imprese che sono state selezionate attraverso CISA per Company. Le imprese sono state selezionate con questi bandi. Quindi una presenza molto forte, molto pervasiva all'interno del Paese, che era quello che ci eravamo posti. Il lavoro che stiamo facendo, come diceva Alexander, ha avuto successo in questa direzione. Abbiamo utilizzato bene i fondi che abbiamo avuto. Io menziono soltanto un aspetto perché era il punto 1 di quella lista di cose che abbiamo detto. Abbiamo detto che avremmo meglio equipaggiato i laboratori italiani attivi in questo settore. Abbiamo finora impegnato 25 milioni in attrezzature. Con la fine del progetto arriviamo a 40 milioni impegnati in attrezzature. Questo è un salto, scusate il bisticcio, quantistico, quantitativo, quantico del sistema. Ora i nostri laboratori, i nostri ricercatori sono meglio attrezzati, sono più competitivi. Vorrei che non si sottolineasse che abbiamo fatto una ripulita di tutti i sistemi criogenici con l'elio, che è un game changer del sistema, perché l'elio tra un po' non c'è più, come tutti sappiamo, e costa troppo. Abbiamo ripulito completamente il laboratorio, quasi totalmente i laboratori, qualcuno ha preferito riciclare e comprimere, fair enough, ma abbiamo ridotto significativamente il bisogno in questo senso, che per una ricerca spesso criogenica è una cosa importante. Questo era il primo obiettivo e possiamo dire a posteriori, visti anche i risultati, è un risultato che noi riteniamo di aver raggiunto, e in questo ci ha confortato anche il nostro gruppo di valutatori. Questo è l'ultimo rapporto. Come avete sentito, i rapporti sono, come forse dolorosamente sapete, immagino, i rapporti sono trimestrali, una frequenza alta per questo tipo di attività, e noi la seguiamo con religiosa e rigorosa precisione, utilizzando al massimo anche la pazienza e la cortesia dei nostri revisori, che ricevono 200 pagine di testo ogni 3 mesi, 500 pubblicazioni in più e così via. Come vedete, questo è l'outcome dell'ultima valutazione. I milestone completati sono quelli che finivano nel periodo, hanno avuto la valutazione positiva. Quelli ancora in corso, quelli che sono ancora partially completed, quelli che sono ancora in vita, hanno comunque avuto una valutazione positiva sull'andamento. Complessivamente abbiamo avuto valutazione positiva, e questo significa che il programma viene continuato e abbiamo ricevuto i trasferimenti del caso. Il professor Golubov menzionava questo commento finale, che secondo me è importante, e che deriva in parte dalla struttura del rapporto. Noi dobbiamo fare un rapporto selettivo su ogni singolo milestone, e quindi si presentano i vari filoni separatamente, ma manca un quadro generale, dicono loro, che in questa fase diventa particolarmente importante, quando ci avviamo verso il definire il profilo di NQSTI per la sua vita anche nel futuro. E allora abbiamo introdotto un cambiamento importante nel progetto, che è diventato efficace qualche giorno fa. Abbiamo creato un nuovo milestone. uno in più, ai noi, però che è quello il contenitore dentro il quale finiranno questi discorsi, dove noi potremo spiegare qual è la strategia complessiva. E cominceremo proprio definendo i technology centers di NQSTI, quali sono i luoghi che hanno dimostrato la capacità di fornire servizi per tutta la comunità, i luoghi che sono a disposizione di tutta la comunità nazionale per ottenere studi, oggetti, dispositivi, strumenti e che potranno partecipare alla costituzione del backbone di NQSTI. Li abbiamo chiamati Technology Centers, appunto, sapete abbiamo 3 piattaforme tecnologiche e conseguentemente abbiamo identificato i Technology Centers che siano coerenti con queste 3 piattaforme, complessivamente 5 sono questi centri tecnologici che stiamo andando a sviluppare e che riceveranno nella parte finale del progetto delle risorse che saranno risorse a disposizione di chi li utilizza. Chiarifico, non sono risorse che verranno utilizzate dai centri per il loro sviluppo e per le loro attività, ma sono risorse che finanzieranno quanto viene richiesto dall'esterno, dai partner, siano essi imprese o gruppi di ricerca appartenenti. Questo backbone di centri tecnologici, il primo nucleo di partenza, abbiamo una parte relativa allo Spoke 3, la Atom-based Quantum Technology, e abbiamo qui l'Università di Firenze e il CNR. Vedete la tipologia di servizi di ognuno di questi centri è mostrata sotto, non c'è tempo per né vedere tutto il filmato né per entrare in dettaglio, ma avremo modo di continuare a parlare di questo. Abbiamo poi la parte fotonica, e qui di nuovo la stessa situazione, che abbiamo FBK, BCOC e CNR. Abbiamo poi superconduttori, Università di Napoli e CNR Spin. Di nuovo un po' di belle foto colorate, ma sono cose che conosciamo e vedete i servizi che sono indicati come disponibili presso quella struttura. Abbiamo quindi semiconduttori, qui c'è Scuola Normale, CNR, Istituto Italiano di Tecnologia, qui la produzione di tutti i tipi di cristalli, 2D, 3D, 1D, con tutte le tecniche pietraziali possibili e le fabbricazioni di dispositivi completi. E poi abbiamo uno spoke in cui è coinvolta pesantemente l'industria che fa parte di NQSTI, basato su Sapienza, che c'è sempre questo rumorino iniziale che mi inquieta, Fabio, ma comunque. E qui abbiamo i servizi principali della tipologia di attività. E tutto qui? No. Questo è tutto quello che si può fare in questo momento della vita di NQSTI, perché in questo momento noi possiamo creare, per come è strutturato il progetto, questi centri solo basandoci su quelli che sono i 20 iniziali, d'accordo? Ma è abbastanza evidente che ci sono delle realtà importanti a livello nazionale che stanno emergendo attraverso iniziative regionali, iniziative di vario tipo, che sono candidati ideali per arricchire questo network non appena NQSTI non sarà più all'interno dei condizioni al contorno strette del PNRR. Così come ci aspettiamo che ci siano contatti e rapporti strutturali anche con altri hub che sono all'interno di centri nazionali o altri partenariati con cui si può essere complementari. Tutto questo fa parte di una strategia che è una strategia non solo di logica e di efficacia nostra, ma fa parte anche della legge finanziaria entrata in vigore quest'anno, che dà indicazioni precise in questo senso per lo sviluppo e per la vita degli hub creati con il PNRR. Ad ogni modo, questi siamo noi adesso. Avete sentito attualmente la vita del progetto è fissata fino al 31 dicembre, non più il 30 novembre, 31 dicembre di quest'anno. Vediamo poi come evolveranno queste date durante quest'anno. Per adesso l'obiettivo nostro è quello di realizzare appieno tutti i nostri progetti e obiettivi, anche quelli strutturali, in questo intervallo di tempo per essere pronti tutti insieme alla fase successiva. Chiude con questo la parte, come dire, la prima parte del nostro incontro. Ora passiamo agli interventi di tipo scientifico. Sottolineo che domani abbiamo due altri momenti importanti dal punto di vista strategico e di riflessione comune con i workshop di domani pomeriggio, uno sul trasferimento tecnologico e uno appunto sul dopo PNRR per le scienze e tecnologie quantistiche in Italia. Spero potrete e vorrete essere presenti anche domani. Adesso passiamo alle nostre relazioni di tipo scientifico. Come sempre abbiamo dato agli spoke la facoltà di scegliere una presentazione, il responsabile dello spoke corrispondente presenterà l'intervento. Io vi ringrazio per adesso e do la parola a Marco Liscidini per spoke 1 e 2.
Okay, for the talks, we switch to English. Okay, so as Fabio said, I'm Marco Liscidini, and on behalf of Spoke 1 and also David Vitali with Spoke 2, we invited here Angela Sara Cacciapuoti, who is Associate Professor at the University of Napoli Federico II. She's leading expert in quantum communication, quantum internet. At Spoke 1 and Spoke 2, we deal with the theoretical work at the basis of all the other activities of the other spokes. So let's welcome Angela. She will talk us about the wonderful job she did, in fact, in NQSTI. Thank you very much.
Okay, good afternoon, everyone. It's a pleasure to open the technical part of this plenary. And I'm here, as Marco said, to represent Spoke 1 and 2, that are the two theoretical spoke of NQSTI. And in particular, they deal with complex quantum system. In particular, I'm directly involved. The animation, okay. I'm directly involved in the activity 1.3 and 1.5 that address the design of quantum communication networks and protocols. And I'm doing these activities with my group, which is an heterogeneous group with different and diverse background, ranging from communication engineers to computer science to theoretical physics and electronic engineering. In particular, I think that the most nice feature of my group is that it's a perfectly balanced superposition of female and male states. So this is very good in STEM. In particular, I want to highlight that Dr. Jessica Eliano is an RTDA fully funded by NQSTI, and instead Francesco Mazza is a PhD student, again fully funded by NQSTI. So we are really doing what we promised since we were already on the runway, because traditionally my group is on the design of the protocol stack for the quantum internet, which in the final vision will be a network of networks, of quantum networks, so heterogeneous quantum networks, since they can be owned by different vendors or based on different hardware platform or exploiting different quantum information carriers, for example. By seeing the distributed quantum computing as one of its killer applications, because with this communication infrastructure, we can scale the number of qubits that is limited so far by the technology maturity. Of course, for allowing this heterogeneous network to work together, we need also standards. And in particular, the first RFC, the technical document within the Internet Research Task Force, which is a body within the Internet Engineering Task Force, in March 2023, published this RFC about the architectural principle, in which it was highlighted that the entanglement is the key communication resource that we should exploit for design a quantum communication network. And actually, recently, in our top-down design approach, we interplayed a bottom-up design by leveraging a quantum internet testbed that we are developing based on a source of polarized entangled photons operating in the C-band for obtaining KPI experimental metrics. Okay. So, as I said, the entanglement, we envision the entanglement as the key communication resource, but the entanglement is not just generation and distribution, it affects many network functionality. We exploit the impact of entanglement on different dimensions, but of course, for the time, I will focus on one of a very important aspect, which is the connectivity of the network. So, in the classical network, we are used to deal with connectivity which is based on the physical connection among the nodes. So, in this context, for having the successful transmission of a classical message, you need to use at least once the communication channel. And in this perspective, the neighborhood concept on which many communication functionalities are based is a rigid physical properties. Instead, in the quantum network, once an entangled state is shared, we have a new form of connectivity, which is called entanglement-based connectivity, which redefined the very same concept of topological neighbors, because nodes that are remote in the physical topology can directly communicating, for example, with the teleporting protocol, although they are unconnected. And since this entanglement-based neighborhood concept can be changed at runtime, it can be engineered. So to be more precise, we individuate three types of connectivity. What we call it virtual connectivity. So once an APR pair is shared between two nodes, for example, it acts as a unicast dedicated channel. So at that time, you can, with the local operation and classical communication, transmitting an informational qubit without sending the information carrier encoding this informational qubit physically on the quantum channel. So in this sense, this type of connectivity has a weaker dependence from the instantaneous condition, the instantaneous propagation condition of the quantum channel. That instead is important in the phase of the distribution. But you know that entanglement, once used, is depleted. So once you completed a teleporting protocol, for example, you need to regenerate and redistribute the entanglement. So these impose temporal dynamics in the network that have no counterpart in the classical network. So that you can see in this picture, we have alternation between disconnected and connected slot within the network. Of course, in these temporal dynamics, the type of the distribution schemes that you decide to adopt is very important. For example, we can distinguish between proactive schemes that generate and distribute entanglement once it's depleted, regardless of the traffic patterns. And of course, they require quantum memories, or you have reactive schemes instead that generate and distribute once a communication needs arise. The difference between the two schemes is that the reactive schemes introduce more delays in a scenario already very sensitive to the decoherence. This concept of virtual connectivity is further generalized by swapping operation, because as you can see from the upper figure, nodes that are remote in the physical topology can share a virtual link through swapping operation, so they can act as they are in the same local area network, so direct communication is still possible. Of course, there are no free meals, because the higher is the physical distance between these nodes, the higher is the APR cost that you have to pay. And another aspect that I would like to highlight is that the identities of the node that are involved in this entanglement sharing has to be fixed a priori. So in APR-based, in bipartite entanglement-based network, the capability to adapt to the traffic demand is not so high. If we want to remove this constraint, we have to sort to multipartite entanglement that as a whole act as a shared channel. And according to, of course, the type and the structure of the multipartite states, you can also be able to distillate simultaneously different APR pairs that involves disjoint nodes in the topology, so that you can accommodate parallel communication needs, so that you have a degree of freedom to adapt the neighbor identities to the communication demands. For example, in this picture, you can see on the left the screenshot of the artificial topology at a certain time, and on the right, the topology that has been changed by local operation and classical communication. And you can see that the identities of the node is different. The connectivity is a very important concept in a communication network, because on the concept of connectivity, you can build many network functionality. So it's important that from a network perspective, you are able to exploit this dynamism induced by entanglement. And according to what I'm describing, so on the physical topology, we can build an artificial topology by exploiting multipartite entangled states without any additional physical link deployment. And this artificial topology can be exploited either for intranet connectivity or inter-network connectivity. We have a result in both the domain, but I'm focusing on the network connectivity. So we define some design principle for quantum network covering limited geographical area, the so-called quantum LAN, the QLAN. Why? Because they are envisioned as a building block of what will be the quantum internet, and in particular they are recently gained a lot of attention from the industrial community that is focusing on the development of quantum data centers, for example, in the light of distributed quantum computing. And as I said, the definition of the design principle was to leveraging the entanglement-based connectivity to overcome the limitation induced by the physical topology. This is a zoom on a QLAN. So the first question that we asked to ourselves was, are densely physical connection feasible in quantum LAN as happen in classical LANs, for example, with fat trees topology that are very common in classical LANs? And the answer is no, because for the maturity of the technology, we have sophisticated and resource-intensive setups, so it's for controlling the coherence of the quantum state, the control is very complex. So it's very reasonable and pragmatic to consider simple physical topology like star topology. But this type of star topology induce communication limitation because they prevents the communication between unconnected nodes. So if it's not properly tagged, they can significantly impact on the communication delays, for example, overhead, that is very bad in scenarios sensitive to decoherence. But actually, this centralized design was not only in the topology, but was also accounted in the logic of the QLAN, because we individuate a specialized supernode called orchestrator that was responsible for the generation and the distribution of the multipartite state. And again, why? Because the generation of the entanglement is very expensive and complex. And we left so the other nodes to be lightweights. So we put the intelligence of the network at the orchestrator for simplifying the coordination among clients, for saving in delay, and also simplifying the distribution logic. In particular, we exploit 2 degrees of freedom, the type of multipartite states and also the dimension of the states, in terms of number of qubits retained at the orchestrator. In other words, we maintain the hierarchy not only in the generation of the entanglement, but also in the distribution, since the orchestrator retains some qubits of the entangled state for himself, for adapting the topology, the artificial topology, to the traffic demand. And as a multipartite states, we choose the graph state because they have a unique entangled property. In particular, each graph state corresponds uniquely to a graph. And manipulation on graph states, some important manipulation on graph states like projective measurement through Pauli operators can map into graph operation like vertex deletion or local complementation. In particular, graph states have also been experimentally generated in controlled environment. So if we want to summarize a bit the QLAN prototype, the network intelligence is at the orchestrator that is responsible for generation distribution of the state, and by manipulating the qubit retained at the orchestrator through local operation, it adapts the artificial topology to the traffic demands. Instead, the clients are left lightweights, and it's important to highlight that this type of design goes completely in contrast to what we did in the classical network, where the intelligence is at the host, at the client, and instead the core network is simple. This is the first example. So from a physical star topology, manipulating a linear graph, we end up in artificial bus that connect unconnected physical nodes. So we moved from a client-server model to a peer-to-peer model. And this is the other case. So by properly merging 2 linear graph states, you can obtain this structure of the multipartite entangled states, where the red dots represent the qubit retained at the orchestrator. So what we call a generalized tree-like graph state. And by properly manipulating these qubits, you can end up in the right in the bottom right figures, so a generalization of a ring topology, where that redundant artificial links can be exploited for improving the reliability and adaptability of the quantum network. This is just the research output with the NQSTI acknowledgement if you are curious, and thank you for your attention.
Saltata la concentrazione. So it's now time for the third spoke, and now we move to experimental platforms, and in particular, in this case, to atomic and molecular platforms for quantum technology. So I have the pleasure to have here Francesco Scazza from the University of Trieste, who has put up a new, completely new apparatus on ytterbium atoms. And so, Francesco, please tell us about it.
Everything works. Thanks, Francesco, for the introduction. Good afternoon, everyone. It's really a pleasure to be here, and hopefully the slides will pop up. Shall I do something? No, vedo. Okay, perfect. So good afternoon, everyone, again. So I'm gonna, again, advocate for spoke 3. So I'm mostly gonna talk about why atoms are a very good quantum platform, and I'm gonna show you some example related to what we did in our lab in Trieste. So let me start actually with a citation that dates back to '68, and I think contains basically all objectives of spoke 3, which is quite inspiring, from Hans de Melt. So what Hans de Melt at the time was considering was the reasons why we want to trap and experiment with atoms, and he's trying to sort of draw a list of ingredients that you would want them to have in order to experiment most efficiently with them. So let's just read the highlighted sentences. He's thinking of isolated atomic systems floating at rest in free space for unlimited periods of time and free from any undesired outside perturbations. So that's basically what has been the goal of many cold atom platforms over the years, to basically have atoms as long-lived as possible and as isolated as possible from perturbation. That means cooling them to very cold temperatures and trapping them in vacuum systems. And most of you are that know cold atom systems know how a lab look like. So it's just a huge amount of optics to make this possible. But the goals why you do this, and that's the second part of this citation, is that you want to be able basically to prepare your atomic system in certain particular states that you select to be useful, for example, containing entanglement if you want to perform a quantum circuit, or containing some metrological gain if you want to have them for some metrological application. And also you want to be able to observe the development of these states in time, due to some controlled interactions that you basically apply to them or that naturally happen in a many-particle system. So these two ideas, the fact that you can control them, but you should also be able to measure them very precisely, were some of the central goals of the spoke tree. So the idea of being able to steer quantum system and engineer entanglement in technologically useful ways, and also the way that we could find to improve our methods in measuring the system and extracting information from it, information that must be, since that's the only way we can interpret information, classical. So that happens through a measurement. So this is just to say that already from back then, if you can tame all these aspects, atoms have a huge technological potential. And I'm just going to show you an example here, which shows how things went over the years. And the example is atomic clocks. So those have been first built with, like 2-meter-sized objects back in the 50s. This is a photo from I think, the UK Metrology Center at the time, with these two gentlemen, Essen and Parry. And then over many decades, the same exact system has been miniaturized to the size of a millimeter chip of, I think in this case, gold-plated glass. So these already sort of witnessed the huge development in technology of producing cold atoms. And all these developments were mostly driven by the field that we call precision measurements, so the idea of using atoms as sensor to measure things of the world as precisely as possible. And let me just flash another thing, which is, so in classical computing, there's something that's called the Moore law, which tells us that every, I don't remember, decade, the computing power roughly doubles. Actually, I think it's much less than a decade. There's a corresponding Moore law in atomic clocks, which is an inverse Moore law. So it's basically the precision of clocks over time. And you see this is a log scale. So there's an almost perfect Moore law in how precisely we can measure, in this case, frequency with atomic clocks that happened during the decades. So this is just to basically advocate that developments are going on, and they're, let's say, fast in the last years, and hopefully we can now merge all these precision measurement science developments into something useful also for quantum computing, quantum simulation, and all, let's say, pillars of quantum technologies. And just to give you a number how this plot goes on more recently, we're now at the level of precision in optical clocks of 1 part in 10 to the 19. So, and not stopping, hopefully, anytime soon. So as I said, this field of precision measurement stimulated over the decades a lot of technical developments, and this made possible to think of atoms as full-fledged quantum platforms where you can now use them to implement quantum computers and quantum simulators that are a bit two coins of the same medal. Two sides of the same medal. So in one case, in the case of quantum computers, basically you want to process information digitally, so you want to implement operations that are discrete and programmable, whereas simulators are mostly intended as analog machines, where quantum evolution proceeds by itself in an intrinsically analog way, but still you want to be able to program the system to steer it at will towards some states or some application that those states are useful for. So these three sort of domain, the technology pushed forward by precision measurements and these new, more recent platforms are all part of the same community effort in developing new tools and better tools to basically tame these atomic systems. So I want to just show you what is the frontier now of these systems, which is well represented in these images from recent papers, which is this new generation of machines where atoms can be detected and controlled at the, let's say, at the single quantum level. So at the level where each single particle is visible and possibly even its internal and external states can be controlled. And this is just a gallery, so I have put 4 examples. So we have on the left optical tweezer arrays, where basically you have reconfigurable grids of atoms with one atom in each side of the grid, and you can make them interact and move on each other at will. And you've seen, actually, there was a movie of this platform in the International Year of Quantum video that you have seen before from the Harvard lab of Misha Lukin. Then we have lattice microscopes that are a more condensed matter targeted platform where you put atoms in a lattice to try to imitate the behavior of electron in solids by atoms moving in a synthetic lattice. And we have more variants where you can now basically detect and control single atoms even in free space, or even measure their state not in real space but in momentum space by basically translating position to momentum. So this is just to say it's a very rich playground that is evolving very fast. And since the time only allows me today to focus on one aspect, I decided to focus on one aspect that is essential both to this platform and to Spoke 3 goals, which is how can we perform better measurements of the system resolved down to the single particle. So let me start introducing a bit what do we mean with measuring a many-body wave function. So we're considering systems that have many particles, many quantum particles, and they have many degrees of freedom in general, can be position, momentum, spin, any other internal state. So what we want to do, ideally, is to be able to read out the state of each and every particle in the system, and this will entail basically what amount of information we can extract from this quantum system. So we have our system, the laser doesn't work. We have, this system under a microscope in general, if you want to have local resolution, and we try to extract by light whatever information we can. So a very idealized projective quantum measurement would go this way. We would prepare the system, and in whatever arbitrary state, this would be a superposition of several many-body configurations. And whenever we perform the measurement, we project this, so a projective quantum measurement, we project the system in one of these states. And by repeating this operation many and many times, so over different repetitions of the experiment, we can essentially sample this many-body wave function and try to extract information from whatever large sample we can have. So in this respect, we can now identify what are the, let's say, best things we can hope to have from a projective measurement experimentally. And I wrote all you want and never dare to ask, but of course theorists always dare to ask experimentalists the most science fiction thing. So this never dare to ask is for experimentalists. So you want the measurement to be resolved in the sense that you want to resolve the single quanta, each and every atom in the system, for example, with their position and possibly even their spin, to extract as more complete information as you can. Then you want this measurement to be fast, ideally faster than all time scales in the experiment, such that it doesn't limit the time scale over which the experiment can be carried out. So it should not be a limit on the data rate of the machine, if you wanna intend this as a, for example, in a quantum computer, if you would take an enormous amount of time to measure the final state, the gate time would not be so relevant anymore because you will spend a lot of time just to measure the system. So you want this to be negligible, or let's say equal to the rest of the operations. And also, ideally, you would want this measurement to be non-destructive in the sense that you want just to project the degree of freedom that you're measuring, and you do not want to perturb any other degree of freedom. For example, I want to measure the state of the qubit, and I don't want to kick the particle in momentum because of having measured the spin. So I would like just to have a projection happen, and maybe even continued evolution after that measurement without, destroying the particle out of the system. So if you can get these three ingredients at work at the same time, this opens a world of possibilities for these new generation machines. First of all, you can efficiently extract correlations from the system. For example, even more than two-body correlation, large correlations, string correlations, whatever you can think about that correlates particles with others. You can arrive at measuring what's called full counting statistics. So not just measure mean values or variance of an operator, but measuring the entire statistical distribution of an operator, which in many cases encloses very important information and connects, for example, to entanglement in the system. And just to name more things, you can, for example, also monitor the system continuously, measuring it stroboscopically and induce very new types of dynamics this way. For example, in a quantum computer, you could think of measuring some qubits at some point in time and let the circuit go on. Basically, the measurements become included in the quantum circuit as an operation as others. Of course, again, they have to be fast and non-destructive to work. Now, if you add single control to this paradigm, you could think of basically now operating a clock completely continuously, because you never destroy it and you can continuously measure different parts of it, or go, for example, that's another example I have in this slide, towards what's called measurement-based quantum computation. So some sort of exotic protocol for quantum computation where measurements are included as a fundamental part of the operation of the quantum computer. Okay, so now let me go to some experiments we performed in this direction within the goals of Spoke 3 to improve the way we measure quantum systems. And the atoms we use in our lab are ytterbium atoms. So ytterbium is a quite versatile atom with a sort of helium-like structure with broad and narrow transitions coexisting together, which become very useful for different type of things you wanna do with your atoms. I'm not gonna go into the details, but just think about the fact that broad transitions are very good to scatter photons, for example, to cool the atoms or see them, whereas narrow transitions are very good to control the state of the atom without heating it up. Another feature of ytterbium is that it contains two stable states, one singlet and one triplet state, that you can use as a so-called optical qubit, These are states that have been used for the last decades indeed to realize the most precise clocks in the world. And it means that the transition between them is so narrow that basically you can consider the excited state as infinitely lived. And so you can consider this as a very ideal two-level system that is coherently coupled by laser light. And finally, each of these two states contains within its internal structure a spin state, which is a nuclear spin. So it is very protected from perturbations. It reacts very weakly to electric and magnetic fields on the outside. So it's a very good qubit, a very good physical qubit candidate. And that's why many startup companies around the world have chosen actually ytterbium for their atom-based quantum computers. Now, a reason why we chose it, and that's a bit of a detour from the, let's say, all the measurement things I want to talk to you about today, is that ytterbium can be state selectively trapped because these two states are so different in energy, you can now conceive optical traps that trap one state without touching the other at particular wavelengths. And that's very useful to realize some particular Hamiltonians that are interesting, where two types of particles feature very different mobility and interact with each other. And you can generalize this, for example, to a full-fledged lattice system where one of the two states would be mobile while the other state is sort of pinned at some positions and behaves essentially as impurities in the rest of the system. I'm just going to flash this plot to show you that the tunability of this confinement between the two states is very versatile, but I don't want to absolutely to comment the details of it. There are just recent measurements that make ytterbium a very ideal candidate in this respect. Now, just to give you one proposal that is a long-term goal in our lab is to realize the so-called Kondo impurity model, which is the possibility of pinning a single spin impurity, which is the yellow atom there, in a sea of fermions, which would be the blue state atoms there, also featuring a spin 1/2 degree of freedom. And you want to study essentially how this impurity and its strong interactions with the environment modify and create correlations in the environment itself. That's a very celebrated model that has been studied in condensed matter for 50 years nearly, and its equilibrium properties are quite well known, but its non-equilibrium properties are still debated. So it's a very interesting idea to implement it in cold atoms. And okay, now I'm gonna just quickly advertise that Adriano Amarici tomorrow is gonna talk at 9 exactly about a project where we for the moment simulated this on a classical computer to realize that you need some special tricks to eliminate some parasitic terms in the model that emerge in the atom simulator and successfully basically go back to a behavior that matches the pristine Kondo model, and so you have some hope to actually study it efficiently. So if you want more details, I suggest you to go to this talk tomorrow. Now, about the experiment, coming back to what I want to show you today, these are some photos from the lab. You see, basically the experiment is built around this glass cell that you see in the center of the first picture, and that's where atoms are trapped and cooled and where they are also measured. And in the photo at the lower right, you see this green ball glowing at the center of the cell. That's our cloud of atoms that is at about 10 microkelvin there. It's about 1 billion atoms. And from there, we can trap them individually in the focus of some optical laser beams that behave as single atom traps, essentially, so-called optical tweezers. That is the platform I'm gonna deepen down a bit now. So this is the machine. I'm also not gonna go into the details here. What you need for, let's say, fulfilling the ingredients that I told you before about the ideal measurement is to have a fast experimental cycle, so something that can produce a high data rate as high as possible, and at the same time you want a long lifetime, which is typically limited by the vacuum level in this system. So we made sure to have a compact machine that can perform Hertz repetition of experiments and at the same time achieved a quite good vacuum that gives us a lifetime of about 200 seconds of atoms once they are trapped. And the heart of the experiment is, as I said, this glass cell where we have a high-resolution objective that is this yellowish tube from top, which both projects potentials onto the atoms to trap them, as well as collects the fluorescence light from the atoms to see their position and their state. So the concept of the experiment that I just resume on this slide is to basically trap this cloud of atoms that is the green fog under the objective, then overlap with this green coldish cloud an array of traps that are these dots, and in each of them the atoms will be trapped if they are cold enough, and then collect the fluorescence that they emit if illuminated with some resonant light via the objective, and via a dichroic send this light onto a very sensitive camera that can see the atoms one by one if they emit enough photons. So we can create up to 50 tweezer traps to trap these atoms one by one. And then we perform, so after trapping them, in order to make sure that they're just 0 or 1, there is one trick that you can perform, is to shine light and associate atoms in pairs, such that pairs leave the traps, and thus you are left either with 0 or 1 atom, depending if the initial number of atoms in the trap was even or odd. So we are left via this protocol with a stochastic filling of the traps with 0 or 1 atom, and the atoms that are left there are at around 15 microkelvin. Here I'm showing you some images taken by this CMOS camera after this process has been done. So there are in total 10 traps, but not all of them, as I said, are filled, because this is stochastic. I can just show you some snapshots. I just have 2 because the animations unfortunately don't work, but just believe me, in every shot you can get any number from 1 to 10, but on average, this would be the average image, every side is 50% filled and 50% empty. And we image these atoms, I said, by collecting the blue fluorescence light. However, if you, let's say, work in the usual regime, you also have to cool the atoms in order not to lose them while you scatter photons. And in this particular image, what we did was to use the green light, the same that we used to create the magneto-optical trap called cloud in the beginning, to cool the atoms while we image them. And this guaranteed us to be able to hold them for hundreds of milliseconds while they scatter light, so to have time to collect enough photons. Now I want to discuss a bit what are the imaging techniques that you can use in general to see single atoms. And I will start from the one that I just showed you in the image before, which is what I call here a long exposure technique, and a code name the breeze. So something very delicate, scattering just enough photons to see the atom over a long exposure time, which requires then to have a very weak illumination to not kick the atom out because of illuminating it. It requires trapping it while it scatters photons, and as I said already, it requires cooling it. So all these 3 ingredients pose some limitations on the type of traps that you can choose, the wavelength that you need to use, and how carefully you need to do the whole process, since it's a very delicate balance between cooling and heating, essentially. Another main limit of this technique is that if you have more than 1 atom in a trap, the cooling light will also associate them in pair, as I said. So you can only measure the parity of the atoms. You can measure 0, 1. If you have 2, you will measure 0 again. So this is called a parity projecting technique, which ideally you would avoid because it limits a lot the type of information you can gain on the system. Recently, there's another technique that surfaced in the community that is the analog of, let's say, flash photography as opposed to long exposure photography. So in long exposure, you want to expose long to collect enough photons, even if the illumination is weak. In flash photography, if you think of flash photography in real life, what you want to do is just illuminate the target with a lot of light in a very short amount of time and try to collect that light with your objective as quickly as possible, essentially. And in this way, you can limit the exposure to, let's say, microseconds in the case of atoms, given the velocities they have. And these times are so short that you can basically imagine that even if the atom is moving, you will basically capture the instantaneous position of the atom during the movement. So this requires to have a transition that strongly scatters photons, to have many photons. It also requires to not have dark states into which the atom can decay and become invisible to the light. But on the positive sides, it can be number resolving. It doesn't entail any photo association of pairs because it's so fast that it's faster than the dynamics of photo association. And at the same time, it can work in free space. As I said, it's so fast that even if the atom is flying around, I will just make a flash photo of it and basically record the image of where it was. So it can be combined with time of flight, atoms expanding around, going in momentum space, for example, and even with something that's called matter wave magnification to map back into position space. So now I'm going to show you some images of this at work from the lab. And the main trick that one has to do to make sure that this fast imaging works is to send alternated pulses from 2 different directions, such that sometimes you kick on the left, sometimes you kick on the right, and on average, you don't kick the atom away from the system. So this is a mean image collected in this way, and you see it looks actually very similar to how it looked when we used the cooling. The main difference is that this image is collected over only 5 to 7 microseconds. So it's an extremely fast method, and this checks one of the boxes that I listed in the beginning. And the other thing is that we may expect it to be lossy since we are sending a lot of light, but actually if we are fast enough and we collect little photons, just enough to see the atom, it is surprisingly non-lossy. And I'm going to show you a bit of a complicated image, but let me briefly guide you through it. So this is a histogram of photons detected in image number 1, and then there's a second image coming, and the vertical point, the vertical coordinate is the number of photons detected in image number 2. So if in both images the atom is present, it will scatter many photons in both images, and this forms this large chunk of atoms high up on the diagonal of the image. If an atom instead was present in the first image and then it was lost consequently to this first illumination, it would be in the bottom part of this diagram. And I'm not sure you can see, but there are very few points that are in this bottom right part of the diagram. So this can be, of course, quantified and calculated quantitatively by making histograms such as this one. And here I'm just showing you a summary plot of the fidelity and the probability of losses of this imaging. That we were very happy about, because we can basically get infidelities, so let's say 1 minus the fidelity of 10 to minus 3, so only 1 over 1,000 times we misclassify an atom for a non-atom and vice versa. And at the same time, the losses are also at the level of 10 minus 3, so only 1 time in 1,000 image you lose the atom. And so these numbers basically are extremely good for an imaging that is this fast. So we have basically a fast, lossless imaging. How much time do I have, Francesco, yet? Negative. Okay, so I'm essentially done. Just what I want to show you is that you can repeat this imaging over and over. The only thing you have to take care is that after taking an image, you should cool back the atom down. Otherwise, of course, having scattered photons, it has heated it up. So you can repeat this over and over. In this case, in this image, I show you 10 images consecutively. And if you see the upper curves, the one where we apply cooling, the survival probability remains essentially 1 over many images. And we can go on and on. OK, since time is basically done, I'm going to skip to just highlights from the lab, what is ongoing right now and what will also be part of the NQSTI goals, which is the detection now of many body states with single atom resolution. And what we did is to use this technique now not with atoms trapped in optical tweezers, but with multiple atoms being left free to fly in real space when we switch off the trap. So in this way, you can not only count them, but also see their state, for example, their velocity, if you wait enough time that they have expanded out of the trap. And this is just a gallery of some images where you can count, for example, 5 atoms in the first, 5 atoms in the second, 2 atoms in the third, with a 50 microsecond time of flight, or an opposite regime where we make a very short time of flight and we shine a lot of photons, which is another completely opposite and interesting regime for us, where the atom basically follows a random walk trajectory while scattering photon. And we're trying to understand also from a quantum optics point of view if this process of the atom random walking around is really a Brownian motion or there is some subdiffusive behavior to it. So stay tuned for more updates on this technique applied to multi-atoms. So with this, I want to thank the whole team that worked hardly on this, especially Alessandro, Omar, and Riccardo, who are the PhD students in the lab. And of course, I want to thank you for your attention. And also advertise a postdoc position to this very wonderful community. Hopefully, it's a good publicity. Thank you so much.
So thank you very much. We can move now to the next spoke 4 about Photonics platform for quantum technologies. And our today invited speaker is Daniele Sanvito from CNR Nanotech Lecce. He's expert worldwide on strong coupling between polariton, excitons, interaction with light. Daniele, the floor is yours.
Thank you, Fabio. Thank you very much. for the introduction. Thank you as well to give me this opportunity to show to you a bit of what do we do, and also somehow the progress that we made in the activity of this spoke. So the spoke 4, it's about photons. In particular, it's about the generation, the detection, and the manipulation of photons, right? So to have a nice system of quantum technology. Now, the activity that we are involved into is also the activity that I lead, is the activity that regards the manipulation of photons in nonlinear system. And in particular, we as CNN Nanotech, we actually use some hybrid state of photons and matter to be able to sort of control photons in the system. And the final goal is to reach some technology in which we make a waveguide in which a few photons can interact with each other. So what is this hybrid state? Basically, the hybrid state is made by polaritons, which are photon and exciton states in semiconductors. Usually you take light and you confine in a nanostructure, which could be this microcavity, and you can make the electric field of light couple very strongly with the exciton of a semiconductor in like a quantum well, or it could be even an organic molecule. So then what we do is you couple these two states, which is a simple harmonic oscillator, and so that you don't have any more the dispersion of excitons and photons, but actually you have this hybrid state, which is called polariton. It's very interesting that this year is the year that actually Hopfield got the Nobel Prize, and I think Hopfield was the father of polariton to some extent. So why we want to use this particle? Well, first of all, excitons are strongly interacting particles that can give more than 3 orders of magnitude interaction compared to standard nonlinear crystals. You have photons on the other hand, and photons, we know, are really good carrier of quantum information. And finally, they also have a small mass. So we can use this small mass to reach Bose-Einstein condensation in solid-state systems, right? And this can be reached even at room temperature because the mass is extremely light. Now, I'll give you some example of what we do of this microscopic quantum state, and then we will go to more quantum, into more the quantum regime. So just to have an idea, in this graph in which I try to put equilibrium in one line and interaction on the other, lasers are at the extreme left. So these are totally out of equilibrium system in which there are no interaction with the photons they emit. On the other hand, you've got cold atoms. Now, cold atoms, they can make condensate, so it's a bit different from what you have seen before. But still, they are very strongly in equilibrium because actually they last, as you have seen, for milliseconds, seconds even. And they also are very strongly interacting. While polaritons are in the middle, and they are strongly non-equilibrium, so they live for something like from 10 of femtoseconds to 100 of picoseconds. But this is enough for us to see the evolution. And they show some interaction, which can be even strong. Just to give you an idea, there are also Bose-Einstein condensates of photons that are in thermal equilibrium because they use a system that relaxes very fast, but they don't have interaction whatsoever. Okay, so one of the first, let's say, like phenomena of Bose-Einstein condensate is to show superfluidity. So if the particle move at a velocity which is beyond the velocity of sound, you see that they feel the object they cannot pass through. While if they are below this velocity of sound, then they show this superfluid behavior. So they don't feel the obstacle, right? So one of the experiment we did was to excite with a pulse laser. So this lasts for a few picoseconds, yet you are able to see on the left side when the fluid is supersonic, and on the right side when it's superfluid. So if it's supersonic, as you see, you have this fringe of interference, and if it's superfluid, you don't see these fringes anymore. Okay, another advantage to use polaritons is that, of course, they are made by photons. So with photons, you can actually give to the polariton wave function all the information you want. Like you can give intensity and you can give phase. So basically, you have all the wave function well defined. So here is the evolution, for instance, of a vortex state, and you see that it starts with a very close core because the heating length is small. Then expanding, there is this decay of the density, and so the increase of the core size. At the same time, in the phase, you see this rotation of 2 pi, which is the velocity actually of your vortex state, because in a coherent fluid, the velocity field is the derivative of the phase in space. And with that, we can really have all the information we want. So, for instance, in case of a chaotic, excitation of our system, this is a big, pulse that arrive at very high energy and creates many vortices in the system. But you can distinguish between the energy of the vortices and the energy of the waves, which is very, very interesting if you want to study turbulence. For instance, in case of 2D turbulence in, the movie does not work. Let's try again. No. Okay. So in this case, extracting the spectrum of the incompressible part of the fluid, you can see that there is an inverse energy cascade, which is a direct consequence of a clustering of the vortices, which is a bit counterintuitive because actually vortices tends, at least in 3D fluid, to become smaller and smaller in scale. And this is also what you see in the atmosphere of planets or even of Earth. Okay, then let me tell you another interesting feature that you can play with using polaritons, and is the fact that you can nanostructure your device. So at the end of the day, you have the possibility to create band structure, photonic band structure, that becomes polaritonic band structure, and so play with the topology of this band structure to have interesting phenomena and observe them. Like here, for instance, we are studying, we are coupling the counter-propagating mode of a waveguide using this grating, which has got a specific symmetry, so that at the end of the day, you can see the presence over there. Well, okay, so there are this splitting, this gap between these two modes. The top one shows a very lossy state, while the bottom one is called the bound in the continuum state, and it actually shows a state that at k equals 0, for symmetry reason, because it's protected topologically by symmetry, it has a very infinite lifetime. So using this state and trying to condense that, we can observe condensation, as you can see here, at very low threshold. So you can, in theory, you can have lasers that are very efficient. And you see now, well, this is just to show the interaction is given by this blue shift of the full structure that you see at time 0, right? Then at a certain time, you start to emit, to create the condensate. It's all very fast. It lasts for hundreds of picoseconds, but with fast detectors, you can really see it. Then, the last example that I can give you, still using this sort of state, which are strongly topologically protected, you can generate a condensate, you see there, at k equals 0, and then exploiting the optical parametric effect, you can, the same condensate can spontaneously form 2 new states at higher bands. And this means that the second spontaneous symmetry broken can give rise to what is called super solidity. And you see this on this feature, this line that appears like a proper crystal in our condensate. Okay, now let me skip the polariton neural network because I think I'm short in time, and also because I really would like to go to what is the aim of our activity, and is to bring this macroscopic quantum fluid to a single quantum level. So in fact, we would like to reach the single particle interaction in our structures. So the first question we ask, it is already some time ago, is if polaritons are actually good carriers of quantum information. So, with Fabio Sciarrino, actually, we did this experiment in which we created two entangled states of photons, and then we made one of the two photons being transferred into our polariton state. Then it lasts there for as long as it lives in the microcavity, and then it's emitted as a photon again. So this is, of course, to measure and to understand if the quantum coherence is maintained even if we are in a system which has a semiconductor as a base. So in fact, it could be very lossy. And then we found actually that entanglement was maintained. So you can see here that the entanglement of the two photons is identical of the entanglement of a photon with the polariton. Okay, so then we use this, so we were kind of excited to do that, and then we start to play with the single photon in our structure. And together with the group of Rastelli, we got one of his very nice quantum dots that emit at an energy very close to our quantum well. And so we could inject photons from this single quantum dot into the polariton state. Then of course, we increase the repetition rate to have enough light coming out, so that in order to picture somehow the map of the photon in space inside of this polariton system. And this is the photon propagating from top to bottom. You see it can propagate for 200 microns, and at the same time you can really see actually, well, where the photon arrives is sort of saturated. But then this is collected of many repetition of the same experiment. Then there is a structural defect in one point, and if you put this defect on the center of this propagation, you can see that now it appears a sort of interference fringes, and which are given by the collision with the effect, like you see in a quantum fluid that is actually very coherent. And this is because the plane wave is interfering with the wave that is generated by the defect because of the scattering into it. So basically, of course, we find that a single particle can still interfere with itself, both in space and time, which is maybe well understood, but it's very nice to see in this map. So it's like it's a fluid of a single particle. Now let's go more deep into the aim of our activity. So what we do now is we want to create waveguides, so circuits of polaritons in which we are able to inject single photons and see the nonlinearity appearing out of it. Now, this is done with these people in CNR, but also we interact with Dario in Pavia, and again with Armando Rastelli, which is in Linz. And also we have the idea of injecting not photons from outside, but actually photons from inside by using a sample from Sanguinetti, which is in Bicocca, that should have a quantum dot at the beginning of our waveguide. And then with Toninelli in Florence, with Costanza, we also have the plan to put molecules into this system. So let's see what we have. So we spent a long time to try to optimize the waveguide in order to have the maximum performance, because we need really to reduce to minimum the losses of the photon in the system. Not only in the system, but also coupling the photon in and out. So we need to have good couplers, you need good funnels, because you go from 5 micron to 500 nanometers, which is the size of our waveguide. Remember that we need to keep the volume very small to have very high interaction. And also, you need to make curves that actually do not lose photons if you want to have very long interferometers. Okay, so the first sample that we realized, and now this is some time ago, some months ago actually, was just showing a beam splitter. We didn't care much about the losses because we used a macroscopic state of light in order to see if the beam splitter was showing actually strong interaction. And as you can see on the right side, there is what is called self-phase modulation, which is even if you excite at a given energy, so this is the far field of our output, even if you excite at some given energy your waveguide, then after some time of propagation, you see that the energy has changed, has increased. Right? And this is because of the interaction. It's a sort of OPO that is generated inside of the waveguide. But what is more interesting is that we can change the action of the beam splitter, so the output would change depending on the power. And as you see here, the actual at the beginning is 50-50, then it's not 50-50 anymore, then 50-50 again, and then it is changed into the other configuration. So in fact, if this can be done somehow with a small number of photons, then we really can make a quantum gate. So let's try to work with this small amount of photons. To do that, we need to see small variation of the phase in our waveguide. So the first thing is to build an interferometer, like you see here. So this is just a design in which we put a signal at one input, which is split into two arms. And then at the end of the two arms, you collect the light and you interfere the light. This is interfering the far field so that you can see actually the interference. And then, of course, this signal is perturbed by a control beam, which only arrives in one of the two arms. Okay, so this is the realized device. We are super happy that we could see propagation over 2 millimeters. Which is, I mean, maybe for just photonic waveguide, it's not so surprising, but this is, remember, it's a waveguide where there are interactions inside, that it's a semiconductor, and so a part of the losses because of the absorption of the semiconductor, you also have the scattering due to the interaction of photons. And still, you can see the light. Then if you isolate the light, you can also see interference, and we were very careful to have a very few amount of photons in the system. So this is much less than 1 photon per pulse, yet you can see the interference after more than 50 minutes of integration. So the system is very stable. The only problem now is that the fringes are very close together, and that's a bit complicated if you want to see very small variation of phase. So the next step was to work in interferometers that are much shorter, but at least they have the output close together. And this, as you can see there, now shows interference which are well spaced in space, and so that you have many pixels between two maxima. Now, what we did then is to have a control that arrive synchronized and not synchronized with the signal. And as you can see, there is a difference here in the two images. Maybe it's easier to see here. I don't know if you notice, well, it's very small. But yet, so there is something, because then if you do the subtraction of these two images, then you can see that when the control is not synchronized, so there shouldn't be any variation of phase, these peaks are very symmetric. I'm not dwelling why it's like that. And when they are actually arrive at the same time, they see this strong, this asymmetry, right? So the asymmetry is given because the shift is only in one direction. Now, of course, the signal is very noisy, and we've got 1 year to get to the milestone of observing this non-linearity. So there are improvements that will be done, of course, in this time, which is, first of all, on the sample. We want samples that are much less lossy, and now we are trying to build a better one with better quantum wells. We also need a better design. Not because of the coupling or the funneling, but because we need to slow light. At the moment, light is not slowed down enough, so the group velocity is roughly 20, 40 picosecond per micron, which is too long. And it means that when a pulse arrives, it's spread in time, but also in space. And this means that the volume of your mode is too big, and so you've got less interaction. And finally, what we would like to exploit is the effect of dipole-dipole interaction. So recently, in this group in Israel from Rappaport, they have observed that if you apply an electric field to a wide quantum well that has, in which the electron holes can be displaced, then you make excitons not interact by exchange interaction, but by dipole-dipole interaction. And apparently this interaction is so strong that even if this system shows made by ITO on a gallium arsenide, so the waveguide is very shallow. It's also quite large. It's 5 micron instead of being 500 nanometers. And the pulse was even broad in energy. They could observe a hint of a blockade effect. So you see on the right side a G2, and it shows an anti-bunching when the energy is below the energy of the system, and it starts to show a bunching when it is above. And apparently this interaction is more than 100 times more than what we have now. So we really should reach this regime of a few particles interacting in the waveguide. Okay, with that I finished. This is the group in Lecce. You see this picture on the left is kind of a bit old now. So there are new people that arrived, others that have left, but of course they contributed somehow also to this experiment that you have seen. What is interesting that the picture in Lecce is done with everybody smiling, as you can see, because Lecce is cool. And then another thing I would like to do is to advertise this school. It's a school of quantum optics and quantum materials that will be held in Lecce again. So you're all welcome to come. There are many amenities, and the school is super nice. Plus, I hope it will be also sponsored by the NQSTI, so I don't know if we can reach that. So please send students, and that's it. Thank you very much for your attention.
Thank you, Daniele. So we have time for coffee break, and we start again at 5:35. So we have a break of 26 minutes, precisely. Thank you.
Antolini? Ah no, ok, perfetto. Un annuncio.
Nicolò Antolini.
Nicolò Antolini.
have a seat. Okay, so after spoke 3 on atoms, spoke 4 on photons, now it's time for spoke 5 on electron-based systems. And in particular, this spoke is divided in 7 research lines. One of these, line number 5, is involving the study of donors, array of donors in semiconductors. And therefore, I ask Marco Fanciulli, who is here from Milano Bicocca, to present us this topic. Okay, thank you, Marco.
Okay, thank you. Good afternoon, everybody. So I will be talking about a research activity, one of the research activity of the Spoke 5, related to the investigation and exploitation of donors in silicon, or more general group 4 semiconductor, but I will focus on silicon, to realize quantum memories which can be coupled with superconducting qubits or also semiconductor qubits. And okay, so actually memories in quantum technologies are part of all these. Every temperature you will need non-volatile or volatile memories. I will discuss, as I said, the last part, which is related to the quantum memories, but there is also a growing interest and activities in developing non-volatile memory and neuromorphic devices for memory application. Also at a higher temperature stage. These are classical, of course, electronics, is not quantum, but since we need these electronics to operate at a low temperature, there is also a growing interest in developing neuromorphic computing for low temperature application like quantum. But as I said, I will focus on the realization and exploitation of donors in silicon, which is a quite well-established technology for quantum memories to be coupled with the superconducting or semiconducting qubit to realize a quantum Turing machine architecture. So actually the effort is challenging from several points of view anyway. We want to store the information for a long time. The coherence must be much longer than the superconducting qubit, let's say transmons, approximately 300 microseconds, so relatively short compared to what the semiconductor qubit can do. We need to develop donors in silicon with frequencies which can be compatible with the superconductor, so in the range between 2 and 12 gigahertz. We have to have fast readout and write times. So that must be at least as fast as the time scale of a typical qubit gate of the order of 100 nanoseconds. And ultimately, we want to have an efficiency which goes to 1, which means the quantum state must be fully retrieved after the storage. So the idea is to store the information inside the semiconductor array, donors in semiconductor, in silicon, and then retrieve the information back to the superconducting qubit at our request, of course. To achieve this, we need to solve several issues. One is purely material science issues, particularly the coherence time of donors in silicon is determined, also is affected, significantly affected by the content of silicon-29, which is only 4.7% in natural silicon, but it is enough to reduce the coherence time in silicon. So you want to have purified, isotopically purified material. And that is a challenging, also from the material science point of view, is expensive, still is not a broad technology. Therefore, there are several possibilities to achieve this, and I will discuss 2 of them and how we place ourselves in this game, which is, as I said, quite relevant. You need a platform with, say, the silicon-28 purified as much as you can. Purification, let's say, from 800 ppm and below. Then you have to select the donor. What kind of donor are you going to use? The prototype of donor in silicon for quantum technology is phosphorus. Actually, on phosphorus, there are based qubit, where the single phosphorus atom is used as a qubit. But here we're talking about an ensemble, and we want to select the donor in such a way that the properties of this donor are compatible with the superconducting qubit. And I will discuss this in a minute. Other substrates, I will not discuss them, but of course you can also use other substrates like silicon carbide or germanium. That is the material science part. There is another challenge in this part, which is the following. I will discuss mainly disordered array of donors. In current technology, we either diffuse, implant donors inside silicon. Of course, and therefore you have a random distribution of these donors. We are also attempting to realize an ordered array of donors because we think that in that case, the coherence time will be even longer, but that has been not achieved yet. Then you need to design a lumped resonator to couple these donors to the superconducting qubit. So you have to design and you have to select a material which must be magnetic field resilient. I mean, in most cases, you need to apply a small, even small, but not zero field, magnetic field to your system. Therefore, some technology like aluminum-based technologies are not compatible with this idea unless, as I will discuss in a minute, you want to operate at zero field, the donors at zero field, which is also possible, but very often you need a small field to operate. And then we have the setup, the standard, let's say, setup at 2 Kelvin, and then the 20 millikelvin setup in order to investigate these arrays coupled with a resonator coupled with a superconducting qubit, which has still to come. So here first, silicon purification. Here I just want to, a lot of activities going on in order to achieve good purification and also not only the purification of the silicon 28 is important, but also the content of impurities in the silicon, like carbon or oxygen, which are the main impurities in silicon technologies, are affecting ultimately the coherence time. So here is our approach and what we have achieved, or we will hopefully achieve soon, in terms of one first solution is to have epi layer grown by chemical vapor deposition with purified silane. We have a purity of less than 100 ppm, and silicon 30 is not so relevant. It's important silicon 29 because it has a nuclear spin, and therefore we want to get rid of that. With carbon and oxygen content below 10 to the 16 per cubic, which is, let's say, good float zone type of material. Here you can see what other technologies has been doing and other groups have been achieving. Then we have another approach which is still ongoing, and which is to locally, we don't need the silicon 28 purification everywhere. You just need it where you have your memory or where you have your device. So we are considering, we are looking and we are exploiting the idea of using focus ion beam to implant silicon 28 and reach locally and purify locally the silicon in silicon 28 only in region which are about 20 by 20 micron or 30 by 30 micron, only in certain area. And this is something which is currently going on. Here we think that we will reach the purity of less than 10 ppm. And also with focus ion beam, we can also implant directly the donor that we want to exploit, particularly bismuth. So we are well placed in the game all over the world related to this kind of purification issue. Okay, this is the other approach that I mentioned, which is the focus ion beam, and also the fact that we can use focus ion beam to have a quasi-deterministic doping of the bismuth, for example, in this area. And that is something which is still, we have not done it yet. These are just what you can see there. What is this? Here. No? Well, what you can see here are area of the silicon 28 by focus ion beam not implanted with bismuth yet. Because implantation, of course, is creating defects, and we have to get rid of these defects in order to make sure that they will not affect We purified on one hand, we get an advantage on the coherence, but then we get defects which we cannot get rid of, and they will also, of course, affect the coherence time of the spin, of the donor spin. Okay. So then the donor zoology, here I just highlight some of the potential candidate or candidate, but I want to focus on different properties which are important. The energy levels of the donors. Donors usually, effective mass theory, you have approximately 10 of milli-electron volt below the conduction band, but there are deeper donors, like bismuth is a deeper donor, or double donors, like the tellurium. The fact that the energy is lower, it is allowing for a better, higher temperature, for example, operation, if you want to, or other good properties from the point of view of the memory as well. The wave function delocalization is important. The zero-speed splitting is important because if you want to operate with a superconductor, you may want not to have a magnetic field. And then in the last column, you can see what is the zero-speed splitting, and you can see that compatible with the superconducting qubit, we have bismuth, basically, and maybe tellurium. As of today, there are few reports which are reporting this kind of attempt to correlate, to make a quantum memory connected with the superconducting qubit are using bismuth. For several reasons, I will discuss some of them later on. Then the spin, of course, it's important to have long coherence time, but here you have ultra long coherence time, seconds, 10 seconds at millikelvin temperature. Then in some cases, like bismuth and tellurium, you can exploit clock transitions, which means that you have transitions which are insensitive, clock transition for the frequency and magnetic field, and clock transition for the hyperfine interaction, which means that you have transitions which are insensitive to small fluctuation of the magnetic field, so longer coherence time, and also insensitive to changes in the hyperfine interaction, which might be affected by local strain during the device preparation. And that is also quite important. But only tellurium and bismuth in this list are actually offering this possibility. Then the nuclear spin, bismuth has nuclear spin 9.5, so huge Hilbert space that you can exploit, but also tellurium has, for example, only 1/2, and phosphorus also. Arsenic is 3/2. If you have a quadruple moment, if you have a nuclear spin larger or equal than 1, then you also have a quadruple moment, and you can also exploit as a manipulation of the spin the quadruple interaction if, of course, your donors is not sitting in a TD symmetry, but it must be sitting in a lower symmetry, which means that you need then to apply strain and remove the degeneracy. That also, I don't know of any attempt to do that in the literature so far. So we have been working on preparing processes and analyzing the material from the point of view of the structural properties and the coherence time properties for these different materials, like, well, phosphorus is the prototype, as I said, but zero-phase splitting is megahertz, and so is not definitely useful for coupling with the superconducting qubit. Bismuth, tellurium, yes, and then also arsenic can be also exploited. Here is just to show that arsenic, for example, this is a 60 by 26 micron square area where we have implanted the arsenic, and just to show that we can measure this kind of, we are talking about, let's say, 10 to the 5 number of atoms, but we can go even lower in terms of sensitivity. And in the other cases, you see in the other plot here, you can see the 10 lines of bismuth here. Forget about this one. Actually, this is a problem we have to solve, but this is related to defects, still residual defects after annealing. And this is the tellurium, 2 lines. Large zero-phase splitting, only spin 1/2, but that is, as I said, also useful. Another important parameter here is the line width of the resonance, which is about 0.3 millitesla, 0.6. This is natural silicon. Only the phosphorus that you can see here is on silicon 28, 800 ppm. And as you can see, you gain a factor of 10 in terms of, approximately 10 in terms of line width. And narrow line width is very important for the reason I will discuss in a minute. Okay, this is just another example, bismuth in germanium, again, 10 lines. Just want to mention that this is a possibility. So also, we are also exploiting not only bulk silicon, but also silicon on insulator, which is a complication in a certain way, but offers a lot of other opportunities to exploit for this application. The first is that when you implant or you diffuse your donor in bulk silicon, you get a Gaussian distribution of your donors inside the silicon. If you use a silicon on insulator, you get a flat, as you can see here. These are Sims profile for the phosphorus and bismuth, and you can see a flat profile. So much more ordered. They are still disordered, of course, in a plane, let's say, but you have the same concentration approximately all over your silicon on insulator layer. That, we think, is an advantage. We need to prove that by measuring the coherence time, which has not been done yet, but we are in the process of doing it. Also, we discovered that, also in collaboration with the theoretical group of Belita Coiler in Brazil, that when you confine your donors inside this 2D structure, the SOI, when you go below, let's say, approximately 20 nanometer, which is still a useful thickness for quantum memories, then you do not modify the wave function, but you increase the energy, activation energy, so the level from the conduction band to the donor level. And that means that having a lower energy, higher energy, will make the spin less sensitive to electric field variation. And that is something which we would like also to exploit. In addition, you can exploit the SOI with backgating, and which is another way of manipulating the spin electrically inside the silicon. Okay, I was mentioning clock transition. These are, again, those transitions in which you have, this is the derivative of the frequency as a function of the magnetic field, resonance frequency. And when you have this equal to 0, then you are insensitive to changes in the magnetic field, and this is the derivative of the frequency against the hyperfine interaction A. And again, you have this clock transition, which you can exploit. This is for bismuth. You have 10 lines in bismuth, 10 possible transitions, and as you can see here in the plot, when you have the approaching 0 for the derivative of the F or the B, then you really increase significantly your coherence time, and you are less affected by instantaneous diffusion or spectral diffusion. Okay, I'm confused about that. Okay, these are some numbers from the literature on T1 and T2 for the nuclear and the electron spin. Now, you will see numbers which are amazing, like 10 seconds here for the T2, or, well, this is T1. T1 is very long. That was already measured by George Fair back in the 59, I think. And anyway, but one has to be careful on what are these numbers, how they are measured, particularly T2. If you measure by a 2-pulse echo decay, that's okay, because this is how we want to operate the memory. But if you start doing CPMG or other, or you exploit other trick, for example, instantaneous diffusion, you can get rid of instantaneous diffusion by applying a very low power pulse, going almost to 0. And then you extrapolate a T2, which is very long. But then if you want really to manipulate your spin, you cannot use a power of 0. You need to send a pulse with a certain power. So one has to be careful. You report always T2 as long as you can measure, but then that doesn't mean that that particular T2 will be the one that you need to consider for your application, which in this case is, as I said, quantum memory. So these are the numbers that we have for a simple 2-pulse echo with a pulse of pi. So we flip pi, okay, which is the highest power that you can apply to our system. So in a sense, the shortest T2 that we can achieve with this material. The first is the phosphorus with natural silicon, then with silicon-28 purified, and all the others are still on natural silicon. So again, as I said, it's important to report the correct, what kind of methodology is used to extract the T2 in order to make sure that it's compatible to the protocol that you want to use to realize the quantum memory. So we have measured, of course, we have done also instantaneous diffusion measurement, and we also have done CPMG, and we know that we can have much longer T2. The question is, can you then use them in the real protocol that you want to set up for the quantum memory? We are still missing a couple of donors like arsenic and tellurium, but this is underway. So, okay, now we have a series of dopants that we can use, and then we have to couple this spin ensemble with a resonator and ultimately with a superconducting qubit. So then the processes are CMOS compatible. The donor then must be introduced either during the growth or by ion implantation or by diffusion, as I already mentioned. And then the semiconductor we are exploiting is either niobium. We were considering also niobium nitride, but for the moment it's going to be niobium is under construction at the moment, the resonator, to test. All the measurements that I reported here have been done in 3D cavities at 9.5 gigahertz. Now we are preparing a new resonator with broadband where we can also operate at different frequencies and based on a superconducting material. The coupling Hamiltonian is here. What is important here, as you can see, is this C, which is so you get an increase in the coupling, which is related to the fact that you have an ensemble and not a single spin, and also that is related to the G of the ensemble, and that also is related to the half width, half maximum of the cavity and of the spin resonance line. That's why the spin resonance line is important, must be very, very narrow. And here are some consideration about the material. This is the niobium, which is our choice for the moment. And this is the coupling, and as you can see, is inversely proportional to Z, so you need low Z, by about 8 ohm, so high capacitances, and so high Q factor, low impedance. We need the ability to operate, of course, the required field and frequencies, and also we need the ability to tune in and out resonance, the spin. These are some possible design. Actually, this is one of the design we are also attempting with niobium. So the protocol to probing the ensemble then is take the photons from the superconducting qubit, you transfer these photons to the resonator via tunable capacitive coupling, and you need to be able to either tune the qubit, superconducting qubit, and the donor. But to tune the donor, you need to apply an external field. Then you need to tune the resonator in resonance with the spin ensemble and allow the transfer of the photons to be absorbed into the ensemble, which are going to be excited. And at that point, the spin will start to dephase, and then you have the time, the dephasing time, the coherence time of the spin, electron spin inside the silicon, which is, as I said, long. If you go to all those temperature, all those results I mentioned, they were taken, as you saw, at 4 Kelvin, 7 Kelvin. Now we go to, if you go to 20 millikelvin, of course, you have much longer coherence time, even too long. At some point, you want to do something to the system in order to initialize again. So then you have a strong microwave pulse. You can use, again, 2 pulse echo to emit the photon back to the qubit. Now, this 2 pulse echo sequence actually is not very efficient because you are manipulating your spin in the excited state, and that implies noise, basically. So what you actually want to do is a 3 pulse sequence in which you have the first echo, then you have a second sequence to realize the second echo, but you silence that echo, and then you exploit the third echo sequence. This is called ROSE, which means refocusing of silence echo protocol, which will allow for manipulating the ensemble in the ground state, not in the excited state, which means less noise. And this is the protocol that we are going to use in order to have the coupling, to show that we can have a coupling between the quantum memory based on these different materials with a superconducting resonator, and then we need to select which kind of donors in order to select what kind, to couple with the specific qubit based on superconductor, like a flux qubit or a transmon qubit. So define the frequency. So this ROSE is here more in detail. I don't know how much time do I have. Finished? Yes, okay. So, okay, this is the silence echo. So you have the first echo, and then you have the silence echo, and then again you have the state retrieve on demand by the third echo, spin echo sequence. Okay, I just want to finish. I have to close. So I close with this slide then. And the slide is just saying that this array of donors can also be used for something different than quantum memory, which is quantum reservoir computing. And here the idea is to exploit the nuclear spin as the reservoir and the electron spin as the qubit, and you can have interaction between these two, and you can realize a reservoir computing quantum, which has classical application like time series analysis or quantum application like analysis of the purity of a state of a qubit. With that, I conclude, and I thank you very much for your attention.
Good, thank you very much. So I'd like to introduce Federica Mantegazoni as the next speaker, who will be talking on behalf of Spoke 6 on integrated quantum components and Spoke 7 on complete quantum systems. And Federica is a critical mass researcher at FBK. So please go ahead, and a little bit quicker, I think, is the request. So.
Yeah, thank you, Richard. And yes, it's my pleasure. It's my pleasure to end this plenary talk. I try to be quick. I know you're tired, just stay with me for this last talk, where I will try to give you an overview on the activities in Spoke 6 and 7 with a focus on the superconducting platform. So as you know, Spoke 6 and 7 are focused on integration and complete quantum systems, where the first Spoke 6, is coordinated by University of Milano Bicocca, and is dealing with the different platforms. So not only the superconducting one, but also photonics, atom, and so on. While the Spoke 7, coordinated by Fondazione Bruno Kessler, looks at application-oriented developments towards complete quantum system. Now, on the superconducting platforms, we are dealing with many different devices, and here I just would like to give you a flavor of what we are doing with a gallery of examples and images on the devices that are very different. So starting with the superconducting parametric amplifiers, which are amplifiers that can reach the quantum limit in terms of noise. And to do that, we have to introduce some nonlinearity in our circuits and to exploit some parametric processes. We can do that either with the high kinetic inductance materials, as you see in the picture, where we'll build a long transmission line out of, for example, an iobium titanium nitride films, as it is in this case, and then we achieve amplification with very low noise, close to the quantum limit. This nonlinearity can also be implemented with another key element, which are Josephson junctions. And in Spoke 6 and 7, we're also dealing with the Josephson parametric amplifiers. A second example of device are tunable resonators. So also in this case, we make use of these two different key components. We can use kinetic inductance circuits to develop current-sensitive resonators, as you can see in the pictures. So resonators that have a resonance frequency that depends on the current flowing in the circuit. On the other hand, we can also build Josephson-based tunable resonators. Third example are obviously superconducting qubits, and in this case we are following two complementary directions. So we're developing both 2D architectures, meaning planar devices, and 3D architectures where the qubit is coupled to a 3D cavity, superconducting cavity, as you can see in the picture. And finally, we are also going beyond what are the more common devices and exploring unconventional superconducting platforms, for example, studying from the theoretical and experimental point of view what happens to an ensemble of qubits that are making a superconducting network, quantum network. And another example are studies on topological superconducting systems, and in particular, Josephson 2D lattices. So this, I hope, gives you a flavor of the wide range of devices that we are dealing with, that can be used for also a wide range of applications. And here are also just some examples. For example, superconducting parametric amplifiers, being quantum limited amplifiers, are key components to perform a high fidelity readout of qubits in a multiplexed fashion. So if we want to understand if a qubit is in a zero state or excited state, we need to have a very low noise stage, and this can be performed with superconducting amplifiers. These devices can also be used for a completely different task, which is generation of entangled microwave photons. Tunable resonators is another example of a multiplexed system where, for example, we can couple each resonator to one detector or quantum sensor, and that the output, the current output of the sensor, will move the resonance frequency of our tunable resonator, and therefore with one microwave line, we can actually read out many quantum sensors in a multiplexing fashion. For transmon qubits, I don't need to tell you that these are the basic components for logic quantum gates, and in turn, logic quantum gates are basic components for programmable quantum processors. And finally, I already mentioned to you that unconventional platforms can be used to implement quantum networks, for example, in this example, with many flash qubits making out our network. So this is just a very quick flash on everything we are doing, or some examples of what we are doing. This shows that we are on track with respect to what we promised in the project, in the proposal, and all these activities are then declinated in many different sub-activities. I obviously don't have the time to go through, but I would like to point out that in the next 2 days there will be many talks by my colleagues. So please, I warmly invite you to attend these talks and learn more about this. But in the rest of the talk, I would like to give you 2 concrete examples of 2 directions that we are following in Spoke 6 and 7 that, in my opinion, are key directions for the development of superconducting quantum technologies in the country. The first one is more on the technological side. So the goal is to acquire all the technological expertise that we need to build a complete supply chain for superconducting quantum technology. The second direction is more on the scientific side. We want to create scientific excellence to reach relevant and impactful scientific results, which then we can use as basis not only for scientific fundamental research, but also for innovation. So in the rest of the talk, I will just give you 2 short examples for these 2 directions, what they concretely meant. And these are only 2 examples among many that I could bring from Spoke 6 and 7. So starting from the first one, I would like to show you how we were able to integrate building blocks and learn how to build a supply chain which made possible to realize the first superconducting qubit fully made in Italy. So we started 2 years ago learning how to make the basic components for our circuits, our building blocks. And if our colleagues from optics or photonics are dealing with elements like beam splitters, lasers, mirrors, in our case, the toolbox is very different. We need to deal with the transmission lines, couplers, capacitors, and so on and so forth. And here, a key component is the Josephson junctions. As you know, Josephson junctions exhibit a macroscopic quantum behavior thanks to the tunneling of Cooper pairs through a thin insulator between two superconductors. It's a rich dynamics, very interesting physics, but practically we can use this element as a non-linear lossless inductance. And that's exactly what we need to build the anharmonic energy landscape that we need then to make superconducting qubits. So the very first thing we need to learn is how to make these Josephson junctions. And here on the right, I show you very briefly, and I will not go into details, there will be talks tomorrow about this, how we learn in FPK to make aluminum-based Josephson junctions, and how then we were able to integrate them to make planar superconducting qubits. Here is an example of a chip that was developed at FPK in collaboration with Milano Bicocca, and this chip contains 2 qubits. You can learn more about this in the talk tomorrow by Alessandro Irace, but here I will just point out that we are able to integrate our Josephson junctions in a more complex circuit, make this chip, cool it down, and verify that this behaves indeed as a transmon qubit. Finally, after integration, we want to move on towards complete quantum system, meaning that we need to have some cryogenic facility, and we need to build not only the technological expertise, but also the experimental facility that we need for this. And this is an example, again, one example among many others. I show you the FPK cryogenic lab that was possible thanks to the NQSTI fundings, and here you see our dilation refrigerators and the day that we were actually installing the system. So with this example, I hope I could show you that we have a lot of synergy to build a complete supply chain, and we are also now moving on in the future towards a multi-qubit system, both in the planar geometry, as you can see here, and in the 3D geometry. And here you see some pictures from NFN, Legnaro, and Frascati, where they are following this 3D approach. All these efforts are collaborative between different institutions, and we were able to show that we can link different know-hows and expertise to build this common supply chain. This is not only about Spoke 6 and 7, there are obviously many links with other spokes. Exactly 1 year ago, we were listening here to the talk by Francesco Tafuri, who was showing the efforts ongoing in Spokes 5 on the superconducting platforms, and obviously there are many links, both for qubits, but also parametric amplifiers. And then to achieve all these experimental results, we obviously need a strong theoretical support, for example, from Spoke 2, sorry, but also Spoke 1. And in the last example, for the second direction, the more scientific-based direction, I would like to show you exactly an example of collaboration between different spokes, including the theoretical part. And this example has to do with a novel device that we have introduced. We call it a microwave photon energy lifter. What is it? It's a device that does 2 things. On the one hand, it's able to shift the frequency of microwave photons, and on the other hand, is able to create a synthetic frequency lattice, which is very interesting from the fundamental physics point of view. This work was possible thanks to the collaboration between the FBK experimental group in Trento with other experimentalists in Trento, both from Spoke 6 and 7, collaboration with Milano Bicocca, again Spoke 6, and collaboration in particular with 2 theoretical physicists, Gianluca Rastelli, who is here, and Jacopo Carusotto, from CNR, Spoke 2. So I think this is really a nice example of synergies, and I would like to dive a little bit in very short time in the physics of this device. So again, we are developing and exploiting our 2 building blocks, in this case, Josephson junctions and resonators. We are merging them, and we are making a Josephson tunable resonator. So device with a resonance frequency that depends on an external parameter. In this case, the parameter is the current that is flowing through this modulation coil. And in the plot, you can see how the resonance frequency depends on the current in the modulation coil that in turn changes the flux in our squid loop and therefore the resonance frequency of the device. On the right, you see a picture of the actual device that we fabricated, and we could model the dynamics thanks to the support from the theory side. If we look at the dynamics and we simulate what this device can do, we see that if we send one microwave signal that is there centered at 0, and then we apply a modulation with a square wave, according to the amplitude of this modulation, we can shift up, or if you want, lift up the energy of the photons in our resonator. And this means that from an external knob at room temperature, we can regulate the frequency of our signal. We made the device in our clean room, we cool it down at millikelvin temperature, exploiting all the technological expertise and facilities that I showed you just in the previous example, and experimentally we can demonstrate that we're able to shift in a tunable way the frequency of our signals. And you can see here, for example, in the cut of the plot, where you see the main signal and then the lifted one far away on the right. Now, what is the impact of this device? This device has these double soles, which on the one hand is very interesting from the fundamental physics point of view, because we could demonstrate, again, thanks to the theory support, that this device is able to generate a synthetic lattice in the frequency space, and we could describe the dynamics of the device in terms of block oscillations. So these represent a very interesting platform for condensed matter physics. On the other hand, this device can also be used for quantum application, and in particular for pulse control, because, again, we are able to shift the frequency of microwave photons, and we are also working on a second-generation device which also ensures pulse preservation, meaning that we are able to send down from room temperature to millikelvin a microwave pulse, and then control it from room temperature, which is very important, for example, for platforms of superconducting quantum computing. In practice, the impact is translated in this case into two publications, one already submitted in review in PRL and one in preparation, one patent already submitted and one in preparation. So I hope that is clear how something that starts from a fundamental research can actually then give a very important contribute in terms of novelty and innovation. And again, this is a synergetic and collaborative effort from different groups and also different NQSTI spoke. And with that, I concluding, showing that there are many links in different spokes. In the examples that I gave you, I was particularly referring to the links between spokes 5, 6, 7, and obviously also spoke 9 and 10. In terms of impact, education, and dissemination, we are building really concrete synergies and collaboration, and what is important, in my opinion, is that we are building a strong national community. So I think I can speak for everyone saying that everybody is looking forward to continue the collaborations and this seed in future projects. Thank you. Hope it was fast enough.
I'm really sorry for this brutal intervention. Thank you for your fabulous speech. The fact is that we have to leave sharp at 6:30, okay? I mean sharp. We're going to be kicked out anyway. So we can use the last 4 minutes to give the awards. Non so perché parlo in inglese, passerei all'italiano, per consegnare i Young Author Awards. Come sapete abbiamo previsto 3 premi. Uno è per il miglior abstract presentato a questo congresso, che è riservato agli under 35, lo consegnerà il nostro presidente a Roberta Satariano, a cui facciamo le nostre congratulazioni. Grazie Roberta. E molti complimenti. Trasmoni era l'argomento comunque, di modo ci sarà, tutti andate a sentire la sua presentazione nei prossimi giorni. Avevamo anche previsto un premio per la miglior tesi in ambito Quantum Science and Technology, non è presente qui perché è già postdoc all'estero, Michele Notarnicola, abbiamo scelto bene, complimenti a Michele. Abbiamo poi previsto la miglior pubblicazione in ambito Quantum Science and Technology. Il lavoro è un lavoro uscito su Nature quest'anno, ci sono 2 primi autori, uno è in questo momento a Parigi se ricordo bene, ma abbiamo la fortuna di avere il secondo co-primo autore, parlo di Giulio Biagioni e Niccolò Antolini che è qui. Complimenti. Complimenti a Niccolò, grazie. Abbiamo anche generato uno special prize uno special award per una proposta di outreach che sarà presentata in uno dei talk domani. La persona è Michela Nazzaro ed è in questo momento giustamente a Parigi all'International Quantum Ceremony che sta avvenendo in questo momento a Parigi, quindi gliela daremo in contumacia. Quindi la giornata si chiude qui, avete ricevuto tutti quanti, quelli che hanno presentazione nei prossimi giorni, un link dove per cortesia depositare le vostre presentazioni in modo che siano... arriverà il link e vi preghiamo di farlo per i prossimi 2 giorni. Ci vediamo domani, grazie mille, buona serata.